Welcome back. Tonight, we're drifting through the realm of Saturn, the ringed wanderer, the jeweled giant, the planet that looks like something from a dream. If you enjoyed this journey, a quick like and subscribe helps others find their way here too. Now, let's begin. Let's start with something simple, something to ground us. Saturn is the second largest planet in our solar system, nearly 9.5 times wider than Earth. If you were to line up 9 Earths side by side, you'd almost span Saturn's equator. Almost, but not quite. Here's another way to picture it. If Earth were the size of a grape, small enough to hold between your fingers, Saturn would be roughly the size of a basketball. You could cradle Earth in your palm, but Saturn would need both arms just to carry. The scale is hard to grasp at first, but that's part of what makes it beautiful. We live on something so small, orbiting a star in a solar system where giants like Saturn exist, spinning quietly in the dark, waiting for us to notice them. And we did notice. Even the ancients saw Saturn, though they had no idea what it truly was. To them it was just a bright dot, moving slowly across the sky, patient and distant. They couldn't have known that this dot was a world nearly 10 times the width of their own, wrapped in rings of ice, surrounded by moons, holding mysteries we're still unravelling today. Those rings, the ones that make Saturn unmistakable, are made almost entirely of water ice, with some rocky debris mixed in. Not metal, not dust, not some exotic cosmic material, just ice, frozen water. The same stuff that forms on your windshield in winter. Yeah, that clinks in your glass on a hot day, that falls from the sky as snow. Think of them as cosmic snowbanks, orbiting the planet, glittering in the sunlight like frozen rain suspended in space. Each particle catching the sun's light, reflecting it back, creating that brilliant glow we see through telescopes. Some of those particles are no bigger than grains of sand. Others are the size of houses, tumbling slowly through the void, colliding occasionally, breaking apart, reforming. Part of a dance that's been going on for millions, maybe hundreds of millions of years. It's strange to think about, isn't it? That something as familiar as ice could create something so extraordinary when scattered across hundreds of thousands of miles of space. Water, in a different context, becomes art, becomes architecture, becomes one of the most iconic sights in the entire solar system. Here's where Saturn gets even stranger. Despite being huge, despite being a giant among planets, Saturn is the least dense planet in our solar system, less dense than water. If you could find an ocean large enough, Saturn would theoretically float on it. Let that settle for a moment. A planet, floating, like a beach ball in a pool. Of course, there is no ocean that large, no bathtub in the universe capable of holding Saturn. But the principle stands. Saturn is made mostly of hydrogen and helium, the lightest elements, with just a small, dense core buried deep inside. The rest is atmosphere, gas, layers of clouds and pressure and wind, all spinning together, all held by gravity into the shape of a world. This low density is part of why Saturn is what it is. It's not a solid place you could stand on. There's no ground to walk on, no surface to explore. If you tried to descend into Saturn, you'd just keep sinking, deeper and deeper, the atmosphere growing thicker, the pressure increasing, until eventually you'd be crushed long before reaching anything resembling a floor. Saturn is more like a concept than a place, a collection of gases pretending to be a planet, and somehow it works. Saturn's rings are surprisingly thin, in some places only about 30 feet thick, despite spanning 175,000 miles. It's like spreading a sheet of paper across the width of a football field. Vast in one direction, impossibly delicate in another. Imagine standing at one edge of the rings and looking across. You'd see a flat plane of ice stretching out toward the horizon, particles orbiting in nearly perfect unison. You're held in place by gravity and orbital mechanics. But if you looked at the rings edge on, they'd almost disappear. 30 feet sounds like a lot until you remember how far these rings stretch. The scale makes them paper thin, fragile looking, even though they're made of chunks of ice that could crush you in an instant. This thinness is part of what makes the rings so mesmerizing. They're efficient. They don't waste space in any direction except the one that matters, and every 15 years or so, as Saturn orbits the Sun and Earth moves around in its own orbit, we see the rings edge on from our perspective. For a brief moment, they seem to vanish entirely, reduced to a faint line, almost invisible. Then, gradually, they open up again, tilting back into view, revealing their full breadth. It's a reminder that perspective changes everything, and what seems substantial from one angle can disappear from another. Galileo first observed Saturn's rings in 1610, but his telescope wasn't powerful enough to see them clearly. He thought the planet had ears, or companion moons on either side. He drew sketches, odd bulbous shapes flanking Saturn, trying to make sense of what he was seeing. He didn't know he was looking at rings. The technology didn't exist yet to reveal the truth. Imagine his confusion. Here was something in the sky that didn't fit any known category. Not quite a moon, not quite part of the planet, just these strange appendages that seemed to defy explanation. And then, a few years later, when he looked again, the ears were gone. Saturn appeared round and normal, as if the bulges had never existed. Galileo was baffled. He wondered if Saturn had swallowed its own children, like the mythological god it was named after. What he didn't realise was that he'd seen the rings edge on during that second observation. They were still there, just invisible from his angle, too thin to detect with his primitive telescope. It would take another 45 years before Christian Huygens, with a better telescope, finally identified them as rings. 45 years of mystery, of wondering, of not quite understanding what Saturn was hiding. And even then, the questions didn't stop, they just got more interesting. A day on Saturn lasts only about 10.7 hours, making it one of the fastest spinning planets. Think about that. A full rotation, sunrise, sunset, and back around again, in less than half an Earth day. If you lived on Saturn, which of course you couldn't, you'd experience more than 2 complete days for every one of ours. This rapid rotation creates powerful winds and contributes to the planet's slightly squashed shape. When something spins that fast, centrifugal force pushes the equator outward, making Saturn wider at its middle than from pole to pole. It's not quite a sphere, it's an oblate spheroid, a technical term for noticeably flattened. You can see this in photographs. Saturn looks subtly squashed, like someone pressed gently on the top and bottom. And those winds, we'll talk more about them later, but they're fierce, faster than anything on Earth, whipping around the planet in jet streams that can last for decades, maybe longer. All of it driven by that relentless spin, by the planet's internal heat, by the complex interactions between different layers of atmosphere. Saturn is a world in constant, restless motion, turning faster than almost anything else in the solar system, wearing its rings like a skirt that refuses to settle. 1 year on Saturn equals about 29 Earth years, the time it takes to complete one orbit around the Sun. 29 years. A single Saturn year spans almost an entire human generation. A child born at the start of a Saturn year would be approaching 30 by the time it ended. They'd have grown up, gone to school, maybe started a career, all within one lap around the Sun for Saturn. This slow, patient orbit is part of what made Saturn seem eternal to ancient astronomers. While other planets zipped across the sky, Mars with its distinctive red glow, Jupiter with its steady brightness, Saturn moved slowly, almost reluctantly, taking decades to cross the zodiac. The Romans named it after Saturnus, their god of time and agriculture, a deity associated with cycles, with patience, with the slow turn of seasons. It was fitting. Saturn embodied time itself, measured not in days or months, but in the long, unhurried arc of years. And because of this long orbit, Saturn experiences seasons that last about 7 Earth years each. Imagine winter stretching through your entire childhood. Imagine summer lasting from middle school through college. The timescales are alien to us, vast and slow, the kind of patience that only planets can afford. Saturn has at least 146 confirmed moons, more than any other planet we've discovered so far. 146. Some are massive worlds with their own atmospheres, their own weather systems, their own geological stories. Others are just tiny chunks of ice a few miles across, irregular fragments tumbling through space, probably captured asteroids or remnants of larger moons shattered by ancient impacts. Each moon has a name, a designation, a place in the orbital hierarchy around Saturn. Some were discovered centuries ago, visible through early telescopes. Others were only found recently, spotted in images from space probes, faint smudges against the black, requiring computer analysis to confirm they're real and not just image noise. And there are probably more we haven't found yet, small ones hiding in the glare of Saturn's rings or lost in the shadows of larger moons. It's a crowded system, a family of worlds, all bound to Saturn by gravity, all following their own paths, some crossing, some in resonance with each other, creating patterns and rhythms that have persisted for billions of years. Saturn isn't alone out there. It's surrounded by an entire retinue, a court of moons, each one with its own story. Titan, Saturn's largest moon, is bigger than the planet Mercury. Let that register for a moment. We're talking about a moon, a satellite orbiting another planet, that's larger than one of the Sun's planets. Mercury is small as planets go, sure, but it's still a planet. And Titan surpasses it in size. But Titan isn't just big, it's the only moon in our solar system with a thick atmosphere and stable liquid on its surface. Everywhere else, moons are barren, airless rocks or balls of ice. Titan has weather, it has clouds, it has rivers and lakes, though not of water, of liquid methane and ethane, yet hydrocarbons that exist as gases on Earth, but condense into liquids in Titan's frigid environment. Walking on Titan would be surreal. The sky would be orange, thick with haze, the sun barely visible through the murk. The air would be dense, the gravity weak. You'd feel light on your feet despite the pressure. And if you look down, you might see a shoreline, waves of liquid methane lapping gently against icy rocks, under a sky that's never been fully clear, on a world that orbits a giant ringed planet instead of a star. Titan is alien, but in a way that feels almost familiar, almost like home, if home were colder, stranger, and infinitely more mysterious. Saturn's moon, Enceladus, shoots enormous geysers of water ice into space from cracks in its surface. Geysers, not small puffs or gentle emissions, enormous plumes that reach hundreds of miles above the moon's surface, spraying ice particles into the void like cosmic fountains. These geysers emerge from what scientists call tiger stripes, long fissures near Enceladus's south pole, fractures in the ice where something beneath is pushing through. These plumes create a faint ring around Saturn, the E-ring, made almost entirely of ice particles expelled from Enceladus. The moon is constantly replenishing this ring, feeding it with fresh material, keeping it supplied with frozen water that catches the sunlight and glows faintly in Saturn's shadow. And beneath those tiger stripes, beneath the icy crust, there's almost certainly an ocean, a subsurface sea kept liquid by tidal heating. The constant flexing of Enceladus's interior as Saturn's gravity kneads it like dough. That ocean might contain everything necessary for life: liquid water, organic molecules, energy from the tidal heating. We don't know if anything lives there, of course. We may never know. But the possibility lingers, quiet and tantalizing, in the geysers that spray into space, carrying samples of that hidden ocean into the light where we can study them. Enceladus, a tiny moon barely 300 miles across, might be one of the best places in the solar system to search for life beyond Earth. And it's been doing this for who knows how long, patiently ejecting water into space, waiting for someone to notice. The rings of Saturn aren't solid. They're made of billions of individual chunks, ranging from grain-sized to house-sized. Each piece orbits Saturn independently, following its own path, moving at its own speed, governed by the same laws of physics that keep planets around stars and moons around planets. The rings look solid from a distance, like smooth bands of light encircling the planet, but up close, they'd reveal themselves as a vast swarm, a cloud of ice particles all travelling together but never quite touching for long. Some collide occasionally, gently bumping into each other, redistributing momentum, changing trajectories slightly. Others spiral inward, pulled by Saturn's gravity and electromagnetic forces, eventually falling into the planet as ring rain, a phenomenon we'll explore later. And some particles might have been there since the rings formed, travelling the same orbital path for hundreds of millions of years, unchanged, patient. Part of a structure larger than themselves. It's a bit like a flock of birds if you think about it. Each bird flies independently, but together they create patterns, shapes, formations that look deliberate even though they're emergent. Arising from simple rules followed by thousands or millions of individuals, Saturn's rings are the same. Billions of pieces of ice, each following gravity and momentum, together creating something that looks designed, intentional, almost impossibly beautiful. But there's no designer, just physics, playing out across cosmic distances, creating art from chaos. Saturn's atmosphere is mostly hydrogen and helium, the same basic ingredients as the Sun. In a sense, Saturn is a star that never quite made it. Not massive enough to ignite nuclear fusion in its core, not hot enough to start burning hydrogen into helium and releasing the energy that makes stars shine. It's a failed star, if you want to be dramatic about it. Or perhaps it's simply a different kind of object entirely, content being what it is. The Sun has about 1,000 times the mass of Saturn. That difference is everything. It's the difference between a ball of gas that glows and heats a solar system, and a ball of gas that merely exists cold and dark except for what sunlight reflects off its clouds. Saturn is made of star stuff, but it was born too small, formed in a region of the solar nebula where there wasn't enough material to gather, to accumulate, to reach the critical mass needed for fusion. And maybe that's fine. Maybe Saturn is better off this way, a planet instead of a star. A place where moons can orbit without being incinerated, where rings can exist without being blasted away by stellar wind, where complexity can emerge in the form of storms and seasons and orbital resonances. Saturn almost was something else, but it became this instead, and this is extraordinary enough. The hexagonal storm at Saturn's north pole has persisted for at least decades, possibly much longer. We've been watching it since the Voyager missions in the 1980s, and it's still there, still hexagonal, still rotating with the planet's interior. Each side of this bizarre geometric shape is wider than Earth itself, about 9,000 miles from corner to corner, a polygon so large it could swallow our entire planet along just one edge. Storms on Earth are circular, or at least roughly so. Hurricanes, typhoons, your cyclones, they all spin in circles because that's what rotating fluid systems do. They follow the path of least resistance, and in a rotating system that path is circular. But Saturn's North Pole storm is hexagonal. 6 distinct sides, 6 corners, angles that look almost artificially sharp, even though they're made of nothing but wind and clouds, and the complex dynamics of atmospheric flow. Nobody fully understands why it's hexagonal rather than circular. The leading theory involves standing wave patterns created by jet streams at different latitudes, interfering with each other in ways that create stable, geometric shapes. It's possible to recreate similar patterns in laboratory experiments with rotating fluids, but scaling up from a tank on Earth to a planet-sized storm involves complexities we're still working through. The hexagon is real. We can see it, measure it, track it, but explaining it completely, that's still a work in progress. Saturn keeps its secrets, even when it puts them on display. Wind speeds in Saturn's atmosphere can reach 1,100 miles per hour, faster than the speed of sound on Earth. These are among the fastest winds ever measured in our solar system, screaming jet streams that circle the planet in tight bands, driven by Saturn's internal heat and rapid rotation. To put that in perspective, the fastest winds ever recorded on Earth, inside tornadoes, reach maybe 300 miles per hour at most. Saturn's average winds are 3 or 4 times faster than our most extreme weather. And these aren't just brief gusts, they're sustained, constant flows that persist for decades, maybe centuries, i.e. carved into the atmosphere by the planet's rotation and the way heat moves through different layers of gas. The hexagon at the North Pole, those jet streams define its edges. Elsewhere, bands of wind circle the equator, some moving east, others west, creating shear zones where different speeds meet and turbulence erupts into storms. If you could somehow float in Saturn's upper atmosphere, protected from the cold, the pressure, the toxic gases, you'd be swept along at speeds that would tear apart any aircraft we've ever built. The wind wouldn't feel like wind at all. It would feel like being fired from a cannon, a relentless force pushing you forward, never stopping, never slowing, part of a planet-wide circulation pattern that makes Earth's weather seem gentle by comparison. Saturn emits more heat than it receives from the sun, and glowing faintly with its own internal warmth. If you could see in infrared, if you could perceive heat as light, Saturn would shine, not as brightly as the sun, but noticeably, a planet radiating energy into space from some internal source. This heat comes from gravitational compression and helium rain falling through its interior, releasing energy as it sinks toward the core. When Saturn formed, it was hot. All that matter falling together, colliding, compressing, converted gravitational potential energy into heat. Over billions of years, the planet has been slowly cooling, radiating that primordial warmth into the void. But it's not just leftover heat from formation. Inside Saturn, helium is condensing out of the hydrogen atmosphere, forming droplets that rain downward through the planet's interior like metallic precipitation. As these droplets fall, they release heat, friction, compression, the conversion of potential energy into thermal energy. It's a slow process, but it's been happening for billions of years, and it will continue for billions more. Saturn is a heat engine running on its own gravity, converting the gradual collapse of its interior into energy that radiates outward, warming the upper atmosphere, driving those fierce winds, maintaining the temperature gradients that create weather. Eventually, in the distant future, Saturn will cool completely, its interior stabilizing, the helium rain slowing to a stop. But not yet, not for a long, long time. Deep inside Saturn, helium condenses into droplets and rains down toward the core like metallic precipitation. This exotic weather system has been happening for billions of years, yet slowly releasing ancient heat, keeping Saturn warmer than it should be based on sunlight alone. It's hard to imagine. Rain inside a planet, falling through layers of hydrogen so compressed it behaves like liquid metal, droplets of helium sinking through. That strange sea toward a core we've never seen and never will. The pressures involved are immense, millions of times Earth's atmospheric pressure. At those pressures, hydrogen stops behaving like a gas and starts acting like a metal, conducting electricity flowing like liquid. Its atoms press so close together that electrons can move freely between them. And through this metallic hydrogen ocean, helium droplets fall, each one carrying a tiny amount of gravitational potential energy that converts to heat as it descends. It's beautiful in a way, this invisible rain falling in the dark, warming a planet from the inside out, maintaining storms that have raged for longer than human civilization has existed. We can't see it happening. We can only infer it from the heat Saturn emits, from models of planetary interiors, from our understanding of how matter behaves under extreme pressure. But it's there, a slow drizzle in the deep, a gentle rain that never stops. Saturn's rings may be surprisingly young, perhaps only 100 to 400 million years old. This means they formed during the age of dinosaurs on Earth, not when Saturn itself was born. While Saturn has existed for about 4.5 billion years, as old as the solar system itself, its rings might be relatively recent arrivals, cosmic newcomers wearing their age well. We know this because the rings are too bright, too clean, too pure. If they'd been around for billions of years, they should have accumulated dust from micrometeorite impacts, darkening them, coating them in a layer of cosmic grime. But Saturn's rings are brilliantly white, reflecting sunlight with an efficiency that suggests they're made of fresh, clean ice, not ancient, contaminated material. The best explanation is that they're young, formed within the last few 100 million years from some event that shattered a moon or tore apart a comet. It's strange to think that Saturn might have spent most of its existence without rings. For 4 billion years, just a large gaseous planet orbiting the Sun, unremarkable except for its size. And then, relatively recently, geologically speaking, something happened. A moon wandered too close and was ripped apart by tidal forces, or a comet strayed into Saturn's gravitational influence and was shredded. And from that destruction, beauty emerged. The rings formed, settling into their current configuration, creating the iconic image we associate with Saturn today. Temporary jewels on a planet old enough to have seen the solar system's birth. The rings might have formed when a comet or moon got too close to Saturn and was torn apart by gravity. There's a limit, called the Roche limit, inside which tidal forces become stronger than an object's self-gravity. Cross that line, and you don't just get pulled toward the planet, you get stretched, elongated, eventually ripped apart into fragments that spread out along your orbital path, forming a ring. Imagine it from the perspective of that doomed moon or comet. You're orbiting Saturn, stable for now, but gradually your orbit is decaying, one spiraling inward due to subtle gravitational interactions or the drag of Saturn's extended atmosphere. You get closer, Saturn's gravity gets stronger, and then you cross the Roche limit. The side of you facing Saturn is pulled more strongly than the side facing away. The difference, the tidal force, starts to overcome the gravity holding you together. You begin to stretch, cracks form, pieces break off, and finally you disintegrate completely, your fragments spreading out into a disk, the remnants of a destroyed world now orbiting Saturn in elegant frozen ribbons. It's a violent origin for something so beautiful. But violence and beauty aren't mutually exclusive in space. Often they're the same event, viewed from different perspectives, separated by time. The rings are gorgeous now, but they were born from destruction, from the death of something that existed before them, and one day they'll be gone too, rained down onto Saturn, leaving only a memory and perhaps some subtle change in the planet's composition. Saturn's rings are slowly disappearing, raining down onto the planet as ring rain. In roughly 100 million years they might vanish entirely. Saturn's rings are temporary jewels, fleeting on cosmic timescales. Every second, about 2,000 pounds of ring material falls into Saturn's upper atmosphere, pulled down by the planet's magnetic field and gravity, vaporizing as it descends, adding a faint shimmer to the planet's cloud tops. We discovered this ring rain by observing spectral lines in Saturn's upper atmosphere, signatures of water molecules that shouldn't be there based on Saturn's composition alone. The water is coming from the rings, pulled down as charged ice particles interact with Saturn's magnetic field. It's a slow process, but it's constant, relentless, a steady drizzle of ice into the planet below, and at the current rate the rings won't last forever. In 100 million years, maybe a bit more, maybe a bit less, the last of the ring material will have fallen. Saturn will be ringless, just another gas giant, visually similar to Jupiter but smaller. Future astronomers, if any exist, might look at Saturn and wonder if it ever had rings. They might find old images from our era and think them artistic exaggerations, prettified renderings of a plain planet. But we know better. We're living in the brief window when Saturn has its crown, when the rings are visible, spectacular, slowly dying but not yet gone. We're lucky in a way. We get to see them while they last. The Cassini spacecraft orbited Saturn for 13 years, sending back over 450,000 images before diving into the planet in 2017. 13 years of patient observation, circling the planet, swooping close to moons, threading through gaps in the rings, measuring magnetic fields and particle densities and temperatures, piecing together the story of Saturn and its retinue one data point at a time. Cassini revealed Saturn and its moons in breathtaking detail. It showed us Enceladus's geysers up close, tasted the water they ejected, analysed the chemistry. It mapped Titan's surface through the haze, discovered lakes and rivers, watched seasons change over years. It studied the rings from every angle, found gaps and waves and structures nobody had predicted, measured the ring reign, estimated the ring's age. And when its mission was complete, when its fuel was running low and it could no longer maintain a safe orbit, Cassini dove into Saturn's atmosphere to avoid any possibility of contaminating the moons it had spent so long studying. Even in death, the spacecraft protected the worlds it had revealed, burning up in Saturn's clouds, becoming part of the planet it had orbited, its atoms mixing with Saturn's atmosphere, a final gift from humanity to the ringed giant. Cassini is gone now, but its images remain, its data still being analysed, its legacy alive in every paper published about Saturn, every new question raised, every mystery partially solved. Saturn's rings have distinct gaps, including the Cassini division, a 3,000-mile-wide empty band that separates the A ring from the B ring. From Earth, even amateur telescopes can see this gap, a dark line cutting through the bright rings, proof that the ring system isn't uniform but structured, organised by forces that create boundaries and divisions. These gaps are sculpted by the gravitational influence of Saturn's many moons. The Cassini division exists because of Mimas, one of Saturn's inner moons, creating what's called an orbital resonance. Any particle orbiting in the Cassini division would complete exactly 2 orbits for every 1 orbit of Mimas. That 2-to-1 ratio means the particle and Mimas would meet at the same point in space repeatedly, and each time Mimas's gravity would tug the particle slightly, nudging it inward or outward, gradually clearing it out of that region entirely. Over millions of years, this process sweeps the gap clean. It's not that particles can't exist there, it's that they don't stay there. They're gently herded away by gravitational resonance, leaving behind an empty band that looks dark against the bright rings on either side. And this happens throughout the ring system. Dozens of gaps, hundreds of subtle divisions, all carved by the gravitational influence of moons both large and small, creating structure from what would otherwise be uniform chaos. The rings aren't random. They're organised, shaped by invisible forces into patterns that persist for eons. Small shepherd moons orbit within Saturn's rings, using their gravity to keep narrow rings sharp and defined. They're like cosmic sheepdogs, herding particles of ice into neat lanes, preventing them from spreading out and diffusing into space. Without these shepherd moons, some of Saturn's narrower rings would blur and fade within a few million years, as their particles drifting apart losing cohesion. But the shepherd moons maintain them, keeping them confined, giving them structure. The F-ring is the best example. It's narrow, only a few 100 kilometers wide, and it's maintained by 2 small moons, Prometheus and Pandora, orbiting on either side. Prometheus orbits just inside the F-ring, Pandora just outside. Together, their gravitational fields create a corridor where ring particles can orbit stably. If a particle drifts too far inward, Prometheus nudges it back. If it drifts outward, Pandora corrects it. The result is a ring that stays narrow, defined, almost impossibly thin given the chaotic nature of orbital mechanics. It's a delicate balance, constantly maintained, never quite perfect. The shepherd moons themselves aren't in perfectly circular orbits, so their influence varies slightly over time, creating waves and kinks in the ring, structures that appear and disappear, making it one of the most dynamic parts of Saturn's ring system. It's order and chaos existing together, structure emerging from forces that could just as easily create randomness, but instead create something that looks almost intentional, almost designed. Saturn's moon Mimas has a giant crater that makes it look remarkably like the Death Star from Star Wars. The crater is called Herschel, and it's enormous, about 80 miles across on a moon that's only 250 miles in diameter. The impact that created it nearly shattered the entire moon, sending shock waves through Mimas's interior, creating fractures on the opposite side where the energy converged after travelling through the moon's body. Mimas is small, and small moons don't have much structural strength. They're held together by gravity and the mechanical strength of ice, but neither is particularly robust at these scales. When the impactor hit, whatever it was, probably an asteroid or comet, it came close to delivering enough energy to blow Mimas apart completely. But the moon survived, barely, left with a massive scar that dominates one hemisphere, a crater so large it gives Mimas its distinctive appearance. The resemblance to the Death Star is purely coincidental, of course. Star Wars came out in 1977. The Voyager spacecraft first imaged Mimas in detail in 1980, revealing the crater to a surprised scientific community. Nobody had predicted it. Nobody expected a moon to look quite so much like a piece of science fiction. But there it was. Reality imitating art. Or perhaps just demonstrating that the universe has a sense of irony. Mimas orbits Saturn still, carrying its wound, a reminder that survival sometimes means bearing scars that never fully heal. Some of Saturn's smaller moons are shaped like ravioli or walnuts due to accumulated ring material. They're so small that they can't pull themselves into spheres. Gravity isn't strong enough to overcome the structural rigidity of ice and rock at these sizes. Instead, they're irregular, lumpy, their shapes determined by how they formed and what they've accumulated over time. The ravioli-shaped moons, Pan and Atlas are the best examples, orbit within or near Saturn's rings, and over millions of years they've gathered ring particles along their equators. Material settles onto them, building up in a ridge that encircles the moon, making them wider at the middle than at the poles. From a distance they look like two rounded halves pressed together with a seam around the middle, exactly like stuffed pasta floating in space. It's an odd sight, these tiny moons that look nothing like the spherical bodies we're used to. But at small scales, different forces dominate. Surface tension matters. The mechanical strength of ice matters. Accretion matters. Where and how material lands, how it sticks, whether it compresses or builds up. These moons are small enough that their shapes tell stories about their environment, about the ring particles they orbit through, about the slow, patient accumulation of ice over geological time. They're strange, but their strangeness is informative, a window into processes that don't happen on larger worlds. Saturn's gravity is strong enough to hold all those moons and rings, yet only about 91% as strong as Jupiter's. It's the perfect balance, enough to gather a cosmic retinue, not so much to crush itself into something denser, something less diffuse. Saturn's mass is about 95 times Earth's, but spread across a much larger volume, which reduces the surface gravity to close to Earth's own. if you could somehow stand on Saturn's cloud tops, if there were a platform to stand on, which there isn't, you'd weigh roughly the same as you do on Earth, maybe slightly more. Of course, you'd be standing on gas which wouldn't support you, so the point is moot. But the gravitational acceleration at that level is familiar, Earth-like, despite Saturn being so much larger. The low density compensates for the large size, creating a surface gravity that doesn't match the planet's imposing appearance, and that gravity is what holds the entire system together. The rings orbit because Saturn's gravity keeps them from flying off into space. The moons orbit for the same reason, each one held in its path by the invisible force emanating from Saturn's mass. It's a tether, a bond, a relationship between a mass and motion that's been stable for billions of years. Saturn is the anchor, the center, the gravitational well around which everything else revolves, held not by chains but by the curvature of space-time, by the fundamental geometry of gravity itself. The rings are labelled with letters in the order they were discovered, not their distance from Saturn. The D ring is closest to the planet, but the A, B and C rings were found first, so they got the first letters. It's a historical naming convention, not a logical one, the kind of thing that makes sense only if you know the backstory. The main rings, A, B and C, were discovered in the 1600s and 1800s as telescopes improved. The D ring, much fainter and closer to Saturn, wasn't confirmed until the 1900s. The E ring, far outside the main rings and fed by Enceladus's geysers, came later still. And the F and G rings, narrow and faint, required spacecraft to discover. Each letter marks a moment in history, a technological achievement, a step forward in our ability to see what was always there but hidden by distance and faintness. It's a bit like archaeological layers, but in reverse. Instead of digging down and going backward in time, we're looking outward and going forward. Each new ring discovered representing a new capability, a new instrument, a new mission. The alphabet of Saturn's rings is a chronicle of human curiosity, of our gradual peeling back of the layers of mystery that surrounded the planet, one observation at a time, one letter at a time. Saturn's moon, Hyperion, tumbles chaotically through space. Rather than rotating steadily like most moons, its irregular shape and Saturn's gravitational pull create unpredictable, chaotic motion, a mathematical phenomenon where tiny changes in initial conditions lead to vastly different outcomes. Hyperion doesn't spin smoothly. It wobbles, tumbles, flips end over end in ways that can't be predicted far in advance. Most moons are tidally locked, always showing the same face to their planet, their rotation synchronized with their orbit. Hyperion can't achieve that stability because it's not spherical. It's lumpy, irregular, shaped like a sponge or a potato, and that irregular shape means Saturn's gravity pulls on it unevenly. The torque varies depending on Hyperion's orientation, and that varying torque prevents it from settling into a stable rotation. The result is chaos, not in the colloquial sense of disorder, but in the mathematical sense of sensitive dependence on initial conditions. Hyperion's rotation is deterministic, governed by the laws of physics, but it's unpredictable beyond a certain time horizon. You can't know which way Hyperion will be facing a year from now without simulating every moment between now and then, and even small errors in measurement compound into large errors in prediction. It's a tiny demonstration of chaos theory, playing out on a moon-sized stage visible through telescopes, or a reminder that predictability and determinism aren't always the same thing. Ancient cultures could see Saturn without telescopes, naming it after gods of agriculture and time. To the naked eye, Saturn is a bright yellowish star that moves slowly against the background of fixed stars. It doesn't twinkle the way true stars do. Planets have disks, however small, that smooth out atmospheric turbulence. So ancient observers could distinguish it from stars, could track its motion, could recognize it as something different, something closer, something wandering through the zodiac. The Babylonians called it Ninurta, after their god of agriculture and war. The Greeks named it Kronos, after the Titan associated with the harvest and the passage of time. The Romans adopted the Greek identification, but renamed it Saturnus, their equivalent deity, god of sowing and seeds and time's slow turning. All these cultures saw the same object, the same patient wanderer, and associated it with time, with cycles, with the agricultural calendar that measured years in harvests. It makes sense when you think about it. Saturn takes 29 years to orbit the Sun, longer than any other planet visible to the naked eye. It embodies patience, the slow accumulation of days into years, the kind of timescale that agricultural societies understood intimately. Planting, growing, harvesting, storing, all activities that require waiting, planning across seasons, thinking in terms of cycles longer than a single year. Saturn, moving slowly across the sky, became a symbol of that patient time, that measured progression from one season to the next. The Romans named Saturn after their god of time and harvest, which is why we have Saturday. Of all the weekday names derived from planets, this one reminds us to rest and reflect. Sunday for the sun, Monday for the moon, and then we get to Saturday, Saturn's Day, a day that in many cultures marks the end of the work week, a time for rest, for looking back at what's been accomplished, for preparing for the week ahead. There's something fitting about that. Saturn, the planet of time, gets a day dedicated to stepping outside time, to pausing, to not being productive in the usual sense. It's a day for reflection, for rest, for the kind of slow, patient thinking that doesn't fit into the rushed pace of the rest of the week. Maybe that's reading too much into a naming convention. Or maybe the Romans understood something about Saturn that we've forgotten, that time isn't just about constant motion forward, but also about pauses, about moments when we stop and let the world continue without our participation for a while. Saturn orbits slowly, patiently, never rushing, and Saturday, its day, invites us to do the same, to move at Saturn's pace for a while, to remember that not everything needs to happen quickly, that some things, important things, require time to unfold properly. Saturn's iconic rings were likely never seen by ancient astronomers, they're only visible with telescopes. For thousands of years, humans saw Saturn as just another wandering star, bright but unremarkable, moving slowly against the fixed stars, special only because it moved at all. The rings were there, of course, orbiting Saturn just as they do now, but invisible, hidden by distance too faint to see without optical aid. It's humbling to think about. For all of human history up until 1610, Saturn was known but not truly seen. People looked at it, tracked it, named it, incorporated it into myths and calendars and astrological systems, but they had no idea what it actually looked like. They were missing the most distinctive feature, the characteristic that makes Saturn instantly recognizable. That makes it unlike any other planet. The rings were a secret waiting to be discovered, patient in the way that cosmic structures can afford to be patient. And when Galileo finally pointed his telescope at Saturn and saw those strange bulges, those ears he couldn't quite interpret, he was seeing what no human had ever seen before, as he was adding new information to humanity's understanding of Saturn, transforming it from a moving light to a world with structure, with features, with complexity. The rings were still misunderstood, but they were seen, finally, after millennia of invisibility. It was the beginning of truly knowing Saturn, the first step toward understanding what it actually is. In 1612, Galileo was confused when Saturn's ears disappeared. He was seeing the rings edge on. Every 15 years or so, as Saturn orbits the Sun and Earth moves in its own orbit, our viewing angle changes. The rings, tilted at about 27 degrees to Saturn's orbital plane, occasionally present themselves edge-on to us. And when that happens, they seem to vanish. They're still there, of course, but they're so thin, 30 feet in places, that they become invisible, a line too faint to see even through telescopes. Galileo didn't understand this. He saw the ears in 1610, observed them for a while, then looked again in 1612, and found Saturn smooth, round, normal-looking. He was baffled. Where had the appendages gone? Had Saturn absorbed them? Had he imagined them in the first place? He wrote letters to colleagues expressing his confusion, his frustration at this apparently changing planet that refused to make sense. The truth was simpler than he could have guessed with the knowledge available to him. The rings were edge-on, temporarily invisible, and they'd return to visibility as Saturn continued its orbit, and the viewing angle changed. By 1616 they were back, visible again, proving Galileo hadn't imagined them. But the mystery of what they were remained unsolved for decades more. Saturn kept it secret even while revealing glimpses of it, showing just enough to confuse, not quite enough to explain. Christian Huygens first correctly identified Saturn's rings in 1655, 45 years after Galileo's observations. Huygens had a better telescope, better optics, a clearer view. He could see that the structures around Saturn weren't separate moons or attached appendages, but a flat disk, a ring surrounding the planet without touching it. He announced his discovery in the form of an anagram, a common practice at the time to establish priority while keeping details secret until the observation could be confirmed. Later, he published the solution, annulocigitur tenui planio, nusquam coherenti ad eclipticam inclinato, which translates to, "It is surrounded by a thin, flat ring, nowhere touching. Oh, inclined to the ecliptic." Simple words describing something extraordinary. A ring. Not multiple rings yet, that distinction would come later, but a single structure encircling the planet, unprecedented in the solar system as far as anyone knew. Huygens's revelation transformed Saturn from a puzzle into something comprehensible, at least partially. The ears made sense now. The disappearing act made sense. Saturn had a ring that we saw from different angles at different times. It was elegant, beautiful, strange, and real. The mystery wasn't solved completely. Questions about composition, origin, stability would persist for centuries, but the fundamental nature of Saturn's most distinctive feature was finally understood. 45 years of wondering ended by better technology and careful observation. Saturn's rings cast shadows on the planet, creating dark bands that shift with the seasons. When the sun illuminates the rings from one angle, They block some sunlight from reaching Saturn's cloud tops, projecting shadows that move across the planet's surface as Saturn orbits and the seasons change. These shadows are so large they could easily swallow Earth whole, bands of darkness stretching across Saturn's northern or southern hemisphere, depending on the time of year. The shadows shift because Saturn's axis is tilted. During Saturn's northern summer, the sun shines on the northern face of the rings, and they cast shadows on the southern hemisphere. During northern winter, the opposite happens. Shadows fall on the north, and twice per Saturn year during the equinoxes the sun shines edge-on through the rings, creating minimal shadows, or allowing light to reach both hemispheres more evenly. It's a seasonal phenomenon on a planetary scale, visible from spacecraft, measurable in images, a reminder that Saturn experiences time passing just like Earth does, just more slowly. Each season lasts 7 Earth years. The shadows creep from one hemisphere to the other over decades, patient and inevitable, marking time in darkness and light, in the slow geometry of orbits and tilted axes. The temperature at Saturn's cloud tops averages around -285 degrees Fahrenheit, -176 degrees Celsius. It's a frigid world where methane and ammonia form icy clouds instead of water. The cold is profound, absolute in a way that's hard to grasp from Earth's perspective. Water ice, which forms clouds on Earth, is as hard as rock on Saturn. The clouds we see are made of other substances, ammonia ice crystals, ammonium hydrosulfide, are compounds that only exist as gases or liquids on Earth, but freeze solid in Saturn's upper atmosphere. This extreme cold is a function of distance from the Sun. Saturn orbits roughly 9.5 times farther from the Sun than Earth does, and sunlight follows an inverse square law. Twice the distance means 1/4 the intensity. At Saturn's distance, the Sun appears much smaller, its warmth diluted across vast distances, barely enough to heat the upper atmosphere above the background temperature of space. But beneath the visible clouds, temperature increases with depth. The pressure rises, and with it, the temperature. Deep enough, and Saturn's interior becomes hot, thousands of degrees, heated by gravitational compression and the slow rain of helium through metallic hydrogen. But at the cloud tops, where sunlight barely reaches and heat radiates freely into space, the cold is immense, perpetual, a frozen shell around a warm core, insulation that keeps Saturn's internal heat from escaping too quickly. Beneath the visible clouds, pressure and temperature increase until hydrogen becomes a liquid metal. This exotic substance conducts electricity and generates Saturn's magnetic field. It exists nowhere on Earth naturally. You can't make metallic hydrogen in a laboratory without extreme pressures, the kind that only exist inside giant planets, or briefly in diamond anvil cells crushed beyond anything sustainable. Metallic hydrogen is strange stuff. Atoms are pressed so close together that their electrons stop orbiting individual nuclei and start moving freely through the material, like electrons in a metal conducting electricity. It's hydrogen, the simplest element, but behaving in ways that seem alien, unfamiliar, governed by physics that only apply under extreme conditions. And inside Saturn, there's an ocean of it, a layer thousands of miles thick where hydrogen flows like liquid silver, carrying electrical currents, generating magnetic fields, storing heat. This metallic hydrogen layer is why Saturn has a magnetic field. Moving electric charges create magnetic fields, and inside Saturn, Convection currents in the metallic hydrogen layer create exactly that, flowing charges circulating through the planet's interior, generating a dipole magnetic field that extends into space, creating a magnetosphere, shielding Saturn and its moons from the solar wind. It's an invisible structure, detectable only through its effects, arising from processes we can't observe directly but can infer from theory and measurement. Saturn doesn't have a solid surface. It gradually transitions from gas to liquid to possibly a solid core. You couldn't land on Saturn. You'd just sink deeper and deeper until crushed by pressure. There's no ground to stand on, no boundary between atmosphere and planet. Just a gradual increase in density and pressure as you descend, the gas growing thicker, becoming liquid, the liquid becoming denser still, until somewhere deep down, maybe, there's a core of rock and ice. Imagine descending into Saturn. At first you'd fall through thin, cold gas clouds of ammonia and methane, wind howling at impossible speeds. Deeper, and the atmosphere thickens, pressure increases, the gas becoming soupy, then liquid, hydrogen compressed into a sea. You'd be crushed long before reaching this depth, of course, but hypothetically you'd continue sinking, the pressure mounting, the hydrogen transitioning to its metallic phase, conducting electricity, glowing faintly with heat from the interior. And at the very centre, perhaps 10 or 20,000 miles down, there might be a core, rock, ice, metals, the remnants of whatever solid material Saturn accumulated during its formation. Or perhaps not. Perhaps the pressure is so great that even rock behaves like liquid, unable to maintain a solid structure. We don't know for certain. We can't probe Saturn's interior directly. We can only model it, simulate it, make educated guesses based on mass, density, rotation, magnetic field. Saturn's heart remains hidden, unknowable, protected by thousands of miles of hydrogen. Near Saturn's core might be 10 to 20 times more massive than Earth, made of rock and ice. It's buried under thousands of miles of hydrogen and helium, forever hidden from view. We'll never see it. No spacecraft could survive the descent. No instrument could peer through the layers of gas and liquid metal to reveal what lies beneath. Saturn's core is a theoretical construct, inferred but never observed, a piece of the planet that exists in models and calculations but not in photographs. And yet it's probably there. Something has to anchor all that hydrogen and helium. Something has to provide the gravitational seed that allowed Saturn to form in the first place. The core would have formed first, accumulating rock and ice from the solar nebula, growing massive enough to start capturing gas from its surroundings. Once it reached a critical mass, the gas accumulation would have accelerated, runaway accretion pulling in hydrogen and helium until the surrounding nebula was depleted or dispersed. So the core is old, primordial, the original nucleus around which Saturn assembled itself. It's been sitting there for 4.5 billion years, crushed under immense pressure, possibly partially dissolved into the surrounding layers, maybe maintaining its integrity, maybe not. We don't know its exact composition, its temperature, its structure. But it's there, silent and hidden, the foundation of everything Saturn is. The pressure at Saturn's core could be millions of times greater than Earth's atmospheric pressure. At those pressures, even familiar substances behave in completely alien ways. Rock might flow like putty. Ice might exist in exotic crystalline forms that don't occur anywhere on Earth. The laws of chemistry and material science still apply, but the outcomes are strange, counterintuitive, governed by conditions so extreme they're hard to even imagine. Earth's atmospheric pressure is about 14.7 pounds per square inch at sea level. Inside Saturn's core, the pressure might be tens of millions of pounds per square inch, a force so great it would instantly crush anything we could build, any material we know. Atoms are pressed close together, their electron clouds overlapping, their behaviour dominated by quantum effects and degeneracy pressure, the same physics that keeps white dwarf stars from collapsing. It's a hostile environment in the most absolute sense. Not just unsuitable for life, unsuitable for matter to exist in any recognisable form. Everything is transformed by pressure into states we can only predict theoretically. Simulating computers glimpse briefly in laboratory experiments that recreate these conditions for microseconds. Saturn's core is an extreme environment, a laboratory of high-pressure physics, running experiments that have been ongoing for billions of years, and we're only beginning to understand what happens there. Saturn's magnetic field is about 578 times stronger than Earth's, though weaker than Jupiter's. This invisible force field shields Saturn and its moons from solar radiation, creating a magnetosphere, a bubble in space where Saturn's magnetic field dominates over the Sun's. Charged particles from the solar wind hit this magnetosphere and are deflected, flowing around Saturn rather than striking the planet directly. The magnetosphere extends far beyond Saturn itself, encompassing the rings and many of the inner moons. Charged particles get trapped in the magnetic field, spiraling along field lines, bouncing between magnetic poles, creating radiation belts similar to Earth's Van Allen belts, but larger and more intense. These trapped particles can damage spacecraft electronics, pose hazards to any hypothetical future missions to Saturn's moons, and create auroras in Saturn's upper atmosphere when they spiral down toward the magnetic poles and collide with gas molecules. Saturn's auroras are spectacular. They've been observed in ultraviolet and infrared wavelengths, frequencies invisible to human eyes but detectable by instruments on spacecraft and space telescopes. The auroras form glowing ovals around Saturn's poles, thousands of miles across, and are rippling and shifting as the magnetosphere responds to changes in the solar wind. They're a visible manifestation of invisible forces, magnetic fields made tangible through their interaction with matter, a light show playing out in Saturn's upper atmosphere, ongoing and mostly unwatched. Beautiful whether anyone sees it or not. Titan, Saturn's largest moon, has lakes and rivers, but they're filled with liquid methane and ethane, not water. It's the only world besides Earth with stable liquid on its surface, though nothing like our oceans. Titan is cold, about minus 290 degrees Fahrenheit, minus 179 degrees Celsius. Cold enough that water ice is as hard as granite. Cold enough that methane and ethane, which are gases on Earth, condense into liquids and pool in basins, forming lakes and seas. These aren't small puddles. Titan's largest sea, Kraken Mare, it is bigger than the Caspian Sea on Earth, covering about 154,000 square miles. It's deep too. Radar sounding suggests depths of at least 300 feet in some places, possibly much more, and it's not alone. Titan has dozens of lakes, concentrated near the North Pole, filled with liquid hydrocarbons, some connected by river systems that carve channels through Titan's icy landscape. Walking along the shore of one of Titan's lakes would be surreal. The liquid would be clear, transparent, reflecting the orange sky. Waves would lap gently. Titan's winds are usually calm, but occasionally storms would whip the surface into motion. You could skip stones across liquid methane, watch them bounce and sink. You could theoretically sail a boat, though you'd need a pressure suit and heating to survive. It's an alien environment, but one with strangely familiar features: lakes, rivers, coastlines, the same processes that shape Earth's surface, playing out in a completely different chemical context. Titan's atmosphere is so thick and hazy that its surface is completely hidden from ordinary cameras. Scientists need radar and infrared instruments to peer through the orange smog. The atmosphere is primarily nitrogen, like Earth's, but with a significant amount of methane that creates a photochemical haze, a smog produced when ultraviolet light from the sun breaks down methane molecules, and the fragments recombine into more complex organic compounds that drift down through the atmosphere like a slow, perpetual snowfall. This haze is opaque in visible wavelengths. If you looked at Titan from space with your eyes, you'd see an orange sphere, featureless. Yeah, completely uniform except for slight variations in colour. No surface details, no lakes, no mountains, no continents. Just orange haze, layer upon layer, obscuring everything below. It frustrated early astronomers, who could see Titan was large but couldn't see what its surface looked like, couldn't determine if it had features or was just a smooth ball of ice. The Cassini mission solved this problem with radar and infrared cameras. Radar penetrates the haze easily, bouncing off Titan's surface and returning with information about topography, roughness, liquid versus solid terrain. Infrared can see through the haze at certain wavelengths, revealing some surface features, though not as clearly as visible light would. Together, these instruments mapped Titan's surface over 13 years, revealing a world that's remarkably Earth-like in some ways. Dunes, mountains, valleys, lakes, but utterly alien in composition and chemistry. On Titan, gravity is so weak and atmosphere so thick that humans could fly by flapping artificial wings. It would be like swimming through dense air, a surreal experience unlike anywhere else in the solar system. Titan's gravity is only about 1/7 of Earth's, and its atmosphere is about 50% thicker than Earth's, creating conditions where the ratio of atmospheric density to gravity is far higher than on our planet. This combination means that generating lift is easy. A human wearing lightweight wings with a span of maybe 10 or 15 feet could flap them and rise into the air, sustaining flight through muscle power alone. No engines needed, no complex machinery, just wings and effort. You'd fly like a bird, but slowly, ponderously, the thick atmosphere resisting your movements, making every motion feel like pushing through water. Imagine it, orange sky stretching in all directions, hazy and dim, the sun barely visible through the smog. Below you, lakes of liquid methane, icy terrain, maybe dunes of organic compounds shaped by Titan's gentle winds. You'd flap your wings, rise higher, feel the cold air rushing past, except it wouldn't feel quite like rushing, more like flowing, thick and viscous. Flying on Titan would be dreamlike, slow motion, a fantasy made real by the peculiar combination of low gravity and thick atmosphere. It's one of the few places in the solar system where human-powered flight is genuinely possible. Titan's weather includes methane rain, carved river valleys, and seasonal lakes that appear and disappear. It has a complete hydrological cycle, just with liquid hydrocarbons instead of water. Methane evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, and eventually falls as rain. The rain carves channels in Titan's icy surface, flows downhill, pools in depressions, and the cycle continues, just as it does on Earth with water. But the timescales are different. Titan's seasons are measured in Earth years, 7 years per season, because Titan orbits Saturn, and Saturn takes 29 years to orbit the Sun. So Titan's northern hemisphere experiences 7 years of spring, 7 years of summer, 7 of autumn, 7 of winter. The lakes fill and empty over these long seasons, responding to changes in temperature and evaporation rate, always migrating between hemispheres as the sun's position shifts. Cassini watched this happen over its 13-year mission. It saw lakes appear in the north as northern summer approached, saw them grow and connect, saw rainfall events leave dark patches on Titan's surface where rain had moistened the ground. It documented a world where weather happens, where climate shifts, where the landscape changes in response to seasonal cycles. Titan isn't static, it's alive in a geological sense. Active, dynamic, shaped by processes that are still ongoing, still carving new channels, still depositing new sediments, still raining methane onto icy plains. Titan might have a subsurface ocean of liquid water beneath its icy crust, despite the methane lakes above. 2 separate liquid systems, one on the surface, one hidden below, make Titan profoundly strange. The evidence comes from Cassini's measurements of Titan's gravitational field and its rotation. Titan wobbles slightly as it orbits Saturn, and the amount of wobble suggests that the outer ice shell isn't rigidly connected to the interior. There's something fluid between them, allowing the shell to move independently. That fluid is almost certainly water, kept liquid by heat from radioactive decay in Titan's rocky core, and possibly from tidal flexing as Saturn's gravity kneads Titan's interior. The ocean might be tens of miles deep, sandwiched between the ice crust above and a rocky core below, salty enough to remain liquid at temperatures well below water's normal freezing point. It's an environment that might be habitable, at least for microbial life. Liquid water, organic molecules raining down from above, energy from tidal heating. So Titan has layers, methane lakes on the surface, an icy crust below that, a water ocean beneath the ice, and a rocky core at the centre. It's a nested structure, each layer with its own chemistry, its own physical state, its own potential for interesting processes. The surface is cold and alien, but deep down, Titan might be warm and wet. A hidden ocean that's never seen the sun, isolated from the surface by miles of ice, possibly harbouring life we can't yet detect. Enceladus's water gazers contain organic molecules, suggesting conditions that could support life. This tiny moon may harbour one of the most promising places to search for extraterrestrial life in our solar system. When Cassini flew through Enceladus's plumes, literally flying through the geysers, sampling the material they ejected, it detected water vapour, ice particles, near salt, and complex organic compounds, the building blocks of life as we know it. The organics aren't life, they're just carbon-based molecules formed through chemistry that doesn't require biology. But they're the raw materials, the ingredients that life might use if it exists. And the fact that they're present, along with liquid water and energy from tidal heating, makes Enceladus's subsurface ocean a genuinely plausible habitat. It has everything we think life needs: water, organic compounds, energy, and time. Billions of years for chemistry to experiment, for complexity to emerge, for something resembling life to potentially develop. We don't know if there's life in Enceladus's ocean. We might never know without sending a mission specifically designed to answer that question. a mission that could sample the plumes more thoroughly, analyze the chemistry in detail, look for biosignatures, patterns that would be difficult to explain without biology. But the possibility exists, tantalizing and real, in the geysers that spray into space, carrying samples of that hidden ocean into the light where we can study them. Enceladus is small, barely 300 miles across, but it might be one of the most important worlds in the solar system. The ice particles from Enceladus's geysers feed Saturn's E-ring, creating a ghostly band of material. In a sense, Enceladus is constantly recreating part of Saturn's ring system. The E-ring is faint, diffuse, much less dense than the main rings, but it's there, visible in backlit images where sunlight passes through it, revealing a haze of tiny ice particles orbiting Saturn in the same path as Enceladus. Yeah, these particles come directly from the geysers. They're ejected from Enceladus with enough velocity to escape the moon's weak gravity, but not enough to escape Saturn's gravity entirely. So they go into orbit, spreading out along Enceladus's orbital path, creating a ring that's constantly being replenished. Without Enceladus's geysers, the E-ring would dissipate within a few thousand years, its particles falling back to Saturn or being lost to space. But the geysers keep feeding it, replacing lost particles, maintaining the ring indefinitely. It's a beautiful relationship between moon and planet, between geology and orbital mechanics. Enceladus's internal heat drives the geysers. The geysers feed the ring. The ring encircles Saturn, a visible trace of Enceladus's activity, proof that the moon is geologically alive. Right, and all of it is sustained by tidal heating, by Saturn's gravity squeezing Enceladus, converting orbital energy into heat, melting ice, driving the plumes that create the ring. It's a system, interconnected, each part depending on the others. Saturn's moon, Iapetus, is two-toned. One hemisphere is extremely bright, the other extremely dark. The reason for this stark contrast took centuries to understand and involves cosmic dust and ice. When Giovanni Cassini first observed Iapetus in the 1670s, he noticed something strange. The moon was bright when it was on one side of Saturn, faint when it was on the other side. He correctly deduced that Iapetus had one bright hemisphere and one dark hemisphere, and that it was tidally locked, always showing the same face to Saturn. But why? What could cause such a dramatic difference? The answer involves a feedback loop. Iapetus orbits in a region where there's dust, material knocked off Saturn's outer moons by micrometeorite impacts, slowly spiraling inward. This dust preferentially lands on Iapetus's leading hemisphere, the side that faces forward in its orbit, like bugs hitting a windshield. The dust is dark, darkening the ice where it lands. Once the ice starts to darken, it absorbs more sunlight. The increased absorption causes warming. The warming causes ice to sublimate, turn directly from solid to vapor, exposing more dark material beneath and making the surface even darker. This runaway process continues until the leading hemisphere is almost black, coated in a layer of dark, dusty lag that's been accumulating for billions of years. Meanwhile, the trailing hemisphere remains bright, clean ice, barely touched by the dust, creating the stark two-toned appearance that makes Iapetus one of the most visually distinctive moons in the solar system. The dark material on Iapetus may come from dust knocked off Saturn's outer moons by micrometeorites. Over millions of years, this dust settles on Iapetus, painting one side nearly black. It's a slow process, patient, accumulating grain by grain, impact by impact, each tiny collision on a distant moon contributing a microscopic amount of dust to the cloud that eventually finds its way to Iapetus. This dust doesn't fall uniformly. Iapetus's orbit carries it through the dust cloud, and the leading hemisphere, the side facing forward, sweeps up material like a snow plough. The trailing hemisphere is shielded, protected by Iapetus itself, receiving much less dust. And because Iapetus is tidally locked, the same hemisphere always leads, always faces forward, always accumulates dust, while the other hemisphere remains pristine. The result is a moon that looks painted, divided almost perfectly into light and dark regions, with a boundary between them that's surprisingly sharp in places. It's geological art, created by orbital mechanics and time, by the patient accumulation of dust over eons. No intelligence designed it, no artist planned it. It's just physics, playing out over millions of years, creating a pattern that's beautiful precisely because it emerged naturally, without intention, from the simple rules that govern how objects move and interact in space. Saturn's rings have spokes, mysterious dark features that appear and disappear over hours. They might be caused by electromagnetic forces levitating tiny dust particles above the rings. The spokes were first noticed in Voyager images in the 1980s, dark radial streaks across the bright B ring, appearing suddenly, rotating with the rings for a few hours, then fading away. They don't follow orbital mechanics. They rotate with Saturn's magnetic field, not with the Keplerian orbits of the ring particles. The leading explanation involves electrostatic charging. When meteoroids hit the rings, they create dust, tiny particles that can become electrically charged through interactions with Saturn's magnetosphere and ultraviolet light from the Sun. Charged particles can be levitated by electromagnetic forces, rising above the ring plane where they scatter light differently, appearing dark against the brighter background. The spokes form. These persist for a while, then dissipate as the particles fall back to the ring plane or lose their charge. It's a dynamic process, ephemeral, tied to Saturn's magnetic field and seasonal variations in sunlight. The spokes are more common around Saturn's equinoxes, when the sun illuminates the rings edge on and the electromagnetic environment changes. They're evidence that the rings aren't static, that even on hourly timescales there's activity change, processes happening that we're only beginning to understand. The rings look permanent from Earth, unchanging over human lifetimes, but up close they're active, evolving, responding to forces both gravitational and electromagnetic. Some of Saturn's ring particles are as small as smoke particles, others as large as mountains. This incredible range of sizes creates the complex texture we see in detailed images. The small particles scatter light efficiently, creating brightness. The large ones provide mass, gravitational influence, structure. Together they form a size distribution that ranges over many orders of magnitude, from micrometers to meters, possibly even kilometers for the largest chunks. This range exists because of the way the rings formed and evolved. When a moon or comet was destroyed, however it happened, it broke into pieces of all sizes, large fragments, small fragments, dust created by collisions between fragments. Over time, collisions continued, breaking some particles into smaller pieces, occasionally sticking particles together into larger clumps. The distribution evolved, reached some equilibrium between fragmentation and aggregation, won and now maintains itself through ongoing collisions. The smallest particles, the most numerous, but contribute little to the total mass. The largest particles are rare but massive, containing most of the ring system's material, and in between there's a continuum, a spectrum of sizes, each particle following the same orbital mechanics, but interacting with its neighbours differently depending on its size, creating the intricate structure we observe, waves, gaps, clumps, all emerging from the collective behaviour of billions of particles following simple rules. The F-ring, one of Saturn's outer rings, has kinks, braids and clumps caused by nearby shepherd moons. It's constantly reshaping itself, never looking quite the same from year to year. Unlike the main rings, which are relatively stable and change slowly over millennia, the F-ring is dynamic, chaotic, its structure evolving on timescales of months or even weeks. The shepherd moons, Prometheus and Pandora, orbit just inside and outside the F-ring, and their gravitational influence creates havoc. Prometheus, the inner moon, orbits faster than the ring particles, and every orbit it approaches the ring, its gravity tugs on particles, pulling them inward, creating channels and gaps. Pandora, orbiting outside, does the opposite, pulling particles outward. Together they confine the ring, but they also perturb it, creating waves that propagate through the ring material, colliding, interfering, producing the braids and kinks we observe. And it's not just the shepherd moons. There are probably small moonlets embedded in the F-ring itself, objects a few hundred meters across, too small to see directly but large enough to disrupt the surrounding particles. These moonlets create their own structures, their own clumps and gaps, adding to the complexity. The F-ring is a laboratory of gravitational dynamics, a place where we can watch orbital mechanics play out in real time, creating patterns that shift and change, never quite settling into stability. Occasionally, objects as large as kilometers across form temporarily within the F-ring, then dissipate. These ephemeral moonlets are like cosmic ghosts, appearing and vanishing unpredictably. They're not stable, they don't last long enough to become permanent moons, but they're there, briefly, aggregations of ring particles clumping together through gentle collisions and gravitational attraction. The process works like this. In regions where the ring is denser, particles collide more frequently. Some collisions are gentle enough that particles stick together instead of bouncing apart. Gradually, these stuck-together clumps grow larger, accumulating more particles, becoming proto-moonlets. For a while they persist, growing, creating their own gravitational disturbances in the surrounding ring. But then something disrupts them. A close encounter with a shepherd moon, a tidal stress from Saturn, a collision with another clump, and they break apart, dispersing back into the ring. Cassini observed this happening. It saw bright clumps in the F-ring appear, persist for a few months or years, then fade. It saw collisions between these clumps, saw the aftermath spreading out along the ring. The F-ring is a place where accretion, the process that builds moons and planets, is constantly starting but never quite finishing, interrupted before it can create anything permanent. Its creation and destruction in balance, a steady state that looks chaotic but is actually governed by well-understood physics playing out in a particularly complex environment. Saturn's rings create propeller features, small gaps cleared by embedded moonlets too small to see directly. We can detect these hidden objects only by the disturbances they create in surrounding particles. The propellers are exactly what they sound like. Structures shaped like airplane propellers, with a central gap cleared by the moonlet and curved arms extending on either side where particles have been deflected into slightly different orbits. These features are small, yet only a few kilometers across, but they're distinctive enough to spot in high-resolution images. Cassini found hundreds of them, scattered throughout the A-ring, each one marking the location of a moonlet that's probably 100 to 300 meters across, large enough to clear a gap through gravitational interaction with nearby particles, but too small to see directly even in Cassini's best images. The propellers tell us that Saturn's rings are full of hidden structure, that the smooth appearance we see from a distance conceals complexity on smaller scales. There might be thousands of these moonlets, maybe more, embedded in the rings, each one a stepping stone between ring particle and moon, between dust and world. They're not large enough to be stable long term. Eventually they'll either grow into real moons or be disrupted and dispersed, but for now they exist, carving their propeller-shaped signatures into the rings, visible only by their effects on their surroundings. The exact number of rings depends on how you count them, major divisions versus faint ringlets. Some counts list 7 main groups, others over 30, and the finest structure is nearly infinite. It's a question of resolution, of where you draw the line between distinct rings and subdivisions within rings. From a distance, Saturn has maybe 7 or 8 obvious ring groups, the D, C, B, A, F, G and E rings, plus the Cassini division separating B from A. But look closer, and each of those rings contains structure, gaps, waves, variations in density and brightness. The C ring alone has dozens of ringlets, narrow bands separated by gaps, each one potentially countable as a separate ring. The A ring has the Encke gap and the Keeler gap, major divisions plus countless smaller structures, and if you look even closer, with the highest resolution images, the structure continues downward, finer and finer, approaching a continuum rather than discrete rings. At some point you're not counting rings anymore, you're measuring a density distribution that varies smoothly across distance, with peaks and troughs corresponding to what we call ringlets and gaps. The number you get depends on your measurement threshold, on how significant a variation has to be before you count it as a separate ring. Saturn's rings are both simple, a disk of ice around a planet, and infinitely complex, and containing structure at every scale we can observe. Saturn's rings may be the remnants of a Titan-sized moon that wandered too close billions of years ago. An entire world, torn to pieces by gravity, now orbits peacefully as frozen fragments. This is one theory for the ring's origin. Not a small moon or comet, but something massive, something comparable to the moons we see today, destroyed when it crossed the Roche limit and tidal forces exceeded its structural strength. If this happened, it was catastrophic. A moon the size of Titan, or even a fraction of that size, breaking apart would have been spectacular. An event that reshaped Saturn's orbital environment, scattering debris across a wide region, creating collisions and chaos that gradually settled into the ring structure we see now. The main rings contain enough material to form a moon maybe 300 miles across, which is smaller than Titan but still substantial, still large enough to have been geologically interesting before its destruction. Or perhaps the rings are older, primordial, left over from Saturn's formation. Maybe they're material that was prevented from accreting into moons by tidal forces, orbiting inside the Roche limit from the beginning, never able to gather into a single body. The evidence leans toward younger rings, the brightness, the purity of the ice, the measured rate of ring rain. But there's still debate, still uncertainty. Saturn's rings might be ancient or recent, remnants of a destroyed moon, or primordial leftovers. Both stories are possible, and the truth might involve elements of both. Alternatively, the rings might be leftover material from Saturn's formation that never coalesced into moons. They could be primordial, a window into the solar system's violent birth. This theory suggests that when Saturn formed, some material ended up orbiting inside the Roche limit, where tidal forces prevented it from clumping together into moons. Instead, it remained as particles, orbiting independently, gradually settling into a thin disk through collisions that dampened random motions and aligned everything into a flat plane. If this is true, then Saturn's rings are 4.5 billion years old, as ancient as the planet itself, survivors from the era when the solar system was still forming, when planets were sweeping up material and moons were accreting in orbit around them. The rings would be fossils, preserved samples of the solar nebula, as largely unchanged except for gradual contamination by meteorite impacts and cosmic dust. But there's a problem with this theory. The rings are too bright, too clean. Billions of years of meteorite bombardment should have darkened them significantly, mixing in rocky material, reducing their reflectivity. The fact that they're still so bright suggests they're younger, maybe much younger, unless there's some process we don't understand that cleans the rings, that preferentially removes dark material while leaving bright ice behind. The mystery isn't fully solved. Both theories have merit, both have problems, and the truth might be more complex than either simple story allows. The main rings, A, B, and C, contain 99% of the ring system's mass despite being incredibly thin. Almost everything visible in those iconic images is concentrated in these three dense bands. The D ring, closer to Saturn, is extremely faint, barely visible. The F ring is narrow and low mass. The G and E rings are so diffuse they're nearly invisible except in backlit images. All the outer rings combined contain maybe 1% of the ring system's total mass. This concentration makes sense from a stability perspective. The main rings orbit in a region where they're protected from most perturbations, where the orbital environment is relatively stable, where particles can survive for millions or billions of years without being disrupted. The outer rings are more vulnerable. Gravitational interactions with moons, atmospheric drag from Saturn's extended atmosphere, solar radiation pressure all work to disperse particles, preventing them from accumulating into dense structures. So when we picture Saturn's rings, we're really picturing the B ring primarily, the brightest, densest, most massive component. It's the B ring that creates the iconic image, that reflects most of the light, that contains most of the ice. The other rings are interesting, scientifically important, but visually they're accessories, decorations around the main event. And that main event, concentrated in a thin disk barely thicker than a building in places, contains the mass of a 300-mile moon spread across hundreds of thousands of miles of space, creating the illusion of solidity from sheer numbers. Saturn's ring system spans more than 175,000 miles, but averages only 30 feet thick in places. The scale is almost incomprehensible, vast yet impossibly delicate. To visualize this, we imagine scaling the rings down so that their thickness is 1 millimeter, the thickness of a credit card. At that scale, the rings would be about 6 kilometers wide, the size of a small city, but still only 1 millimeter thick. It's a ratio that doesn't exist in everyday objects, a flatness that seems almost impossible. This extreme thinness results from collisions between ring particles. When particles collide, they tend to average out their vertical motion. Particles moving up collide with particles moving down, and the result is that both end up moving more horizontally, more in plane with the ring. Over time, millions of collisions dampen all vertical motion, flattening the ring into a plane whose thickness is determined by the random velocities of particles and the balance between collision rates and gravitational perturbations from moons. The result is a structure that's essentially two-dimensional, a disk so thin that it almost doesn't exist in one dimension, yet stretching across astronomical distances in the other two. It's one of the flattest structures in the solar system, rivaled only by protoplanetary disks around young stars and perhaps some asteroid families. And it's stable, maintained by the constant interplay of collision and orbit, a dynamic equilibrium that's persisted for however long the rings have existed. If you could gather all of Saturn's ring material, it would form a moon only about 300 miles across. Spread across such enormous distances, even a moon's worth of material becomes gossamer thin. 300 miles is small for a moon, smaller than our moon, smaller than Titan or Ganymede or Callisto, comparable to moons like Enceladus or Tethys. It's a substantial body but not enormous, not even close to planetary scale. And yet that mass, distributed across the ring system, creates something that dominates Saturn's appearance, that makes it instantly recognizable, that has fascinated humanity since we first saw it through telescopes. The rings look massive, substantial, permanent, but they're mostly empty space, particles separated by distances large compared to their size, a cloud of ice so diffuse that you could fly through much of it without hitting anything. It's a reminder that appearance and reality can diverge, that something can look solid from a distance but be mostly void up close. The rings are real, the ice is there, the particles exist, but they're not what they seem from Earth. They're a magic trick, an illusion created by distance and numbers, billions of particles collectively reflecting enough light to look like solid bands, even though, individually, they're scattered across a volume that's mostly vacuum. Saturn's rings are tilted about 27 degrees to its orbit, creating changing views from Earth over time. Sometimes we see them wide open, other times they're edge-on and nearly invisible. This tilt is the same as Saturn's axial tilt. The rings orbit in Saturn's equatorial plane, and Saturn's equator is tilted 27 degrees relative to its orbital plane, so the rings share that tilt. As Saturn orbits the Sun, our viewing angle changes. When Saturn is at certain points in its orbit, we see the northern face of the rings, illuminated by the Sun, presented at a wide angle. The rings look broad, spectacular, covering a large angular size as seen from Earth. Half a Saturn year later, about 15 Earth years, we see the southern face, equally spectacular but from the opposite perspective. And twice per Saturn year, at the equinoxes the Sun shines edge-on through the rings, and Earth's viewing angle is also edge-on. The rings seem to disappear, reduced to a thin line, barely visible even through large telescopes. During these edge-on events, we can see details normally hidden by the ring's brightness. Faint outer rings become visible. Small moons near the rings are easier to spot, and the planet itself is visible without the glare of reflected sunlight from the rings overwhelming nearby features. It's a brief window, a few weeks every 15 years, when Saturn appears ringless from Earth, a reminder that perspective shapes perception. The changing appearance of Saturn's rings helps astronomers measure Saturn's precise orbital tilt. Ancient structures become modern scientific instruments when observed carefully enough. By tracking how the rings appear from Earth over decades, measuring the angle at which we see them, noting when they go edge-on, documenting the tilt at different points in Saturn's orbit, astronomers can calculate Saturn's axial tilt with remarkable precision. This seems almost backward, doesn't it? We usually think of modern instruments measuring ancient objects, but here the ancient object, Saturn and its rings, unchanged for millions of years, serves as the instrument, and our changing perspective provides the measurement. The rings act like a protractor in space, their angle telling us about Saturn's orientation, their periodic disappearance marking exact moments when our line of sight aligns with the ring plane. And this information matters for understanding Saturn's history. The axial tilt tells us about past collisions, about how Saturn's orientation has evolved over billions of years, about interactions with other planets that might have shifted its spin axis. The rings, just by existing and being tilted, become a source of data about events that happened long before humans existed, recorded in the geometry of Saturn's rotation and preserved in the orientation of orbiting ice. Saturn experiences seasons lasting about 7 Earth years each because of its tilted axis. Imagine winter lasting your entire childhood, then spring for just as long. For someone born on Saturn, if such a thing were possible, their entire elementary school years might occur during spring, middle school during summer, high school during autumn, college during winter. A single season would encompass what feels like entire eras of human life. These long seasons affect Saturn's atmosphere, its weather patterns, its temperature distribution. During northern summer, the northern hemisphere receives more sunlight, warms slightly, and atmospheric circulation responds. Storm systems shift, jet streams change strength. The hexagon at the North Pole might alter its behavior. Then, over the following 7 years, those changes reverse as autumn arrives. Then winter, then spring again. Cassini observed these seasonal changes over its 13-year mission, watching as Saturn transitioned from northern winter to spring and into summer. It documented how storms appeared and dissipated, how cloud patterns evolved, how the ring's shadows moved across the planet's face. Saturn isn't static. It changes, responds to its seasons, evolves over decades in ways that are predictable in principle but complex in detail. The planet we see today is slightly different from the planet Voyager saw in 1980, and both are different from the Saturn that future missions will encounter. The hexagon at Saturn's North Pole was discovered by Voyager spacecraft in the 1980s. For decades, scientists thought it might be a temporary phenomenon, but it persists. Voyager 1 saw it in 1980. Voyager 2 confirmed it in 1981. Then there was a gap. No spacecraft visited Saturn for 20 years. When Cassini arrived in 2004, the hexagon was still there, still rotating, still maintaining its 6-sided shape. That persistence is significant. Storms on Earth last days, maybe weeks. Hurricanes dissipate when they hit land or move over cold water. Even Jupiter's Great Red Spot, the most famous long-lived storm in the solar system, has been shrinking, changing, possibly dying after centuries of persistence. But Saturn's hexagon shows no signs of weakening, no indication that it's temporary. It's been there for at least 40 years of observation, probably much longer, possibly centuries, possibly millennia. The question is, why? What maintains it? What prevents it from blurring into a circular storm like every other rotating weather system we know? The answer involves the interaction between multiple jet streams at different latitudes, creating standing wave patterns that lock into stable configurations. It's possible to recreate similar hexagonal patterns in laboratory experiments with rotating tanks of fluid, but the lab versions are small, temporary, sensitive to disturbances. Saturn's hexagon is enormous, stable, robust. It's the same physics, but scaled up in ways that make it more stable, more resistant to disruption, more likely to persist for geological timescales. Each side of Saturn's hexagonal storm is about 9,000 miles long, wider than Earth's diameter. The storm is so large it could swallow our entire planet along just one edge. Our planet Earth measures about 7,900 miles in diameter. One side of the hexagon is longer than that. The entire hexagon from opposite corners spans about 20,000 miles, 2.5 Earths across. Try to picture it. A storm system larger than Earth, shaped like a perfect hexagon, rotating every 10.7 hours with Saturn's interior, sustained by winds moving at hundreds of miles per hour. At the centre, there's a vortex, a swirling eye surrounded by the hexagonal structure. The whole thing is visible in infrared images as a temperature pattern, invisible light as a structure in the clouds, persistent and unchanged over decades of observation. It's a planetary scale phenomenon, a demonstration of what happens when you have a fast-rotating gas giant with multiple jet streams and no solid surface to disrupt atmospheric flow. Earth's weather is constrained by geography, mountains, oceans, continents that interrupt wind patterns and create turbulence. Saturn has no such constraints. Its atmosphere is free to organize itself into patterns determined purely by rotation, heat flow, and fluid dynamics, creating structures that persist far longer and grow far larger than anything possible on Earth. The hexagon rotates with the same period as Saturn's interior, hinting at deep atmospheric currents. It's connected to the planet's hidden depths, a visible expression of invisible forces. We can't see inside Saturn, the atmosphere is opaque, the interior inaccessible, but we can measure the hexagon's rotation period, and it matches the rotation rate of Saturn's magnetic field, which is generated deep in the metallic hydrogen layer. This tells us that the hexagon isn't just a surface feature. It's rooted in Saturn's interior, connected to flows that extend thousands of miles down, driven by convection and rotation in layers we can't observe directly. The hexagon is like the tip of an iceberg, the visible part of a much larger circulation pattern that encompasses Saturn's entire atmosphere and possibly reaches down into the metallic hydrogen ocean. Understanding this connection helps us understand Saturn as a whole, not just the upper atmosphere we can see, but the interior structure, the heat transport, the way energy flows from core to cloud tops. The hexagon is a window into Saturn's depths, a marker that lets us trace invisible currents, a sign that what we see on the surface is connected to processes happening in realms we'll never directly observe. Wind speeds at the hexagon's edges reach about 220 miles per hour, defining its sharp corners. The precise physics creating those corners involves rotating fluids and wave patterns. In a rotating fluid like Saturn's atmosphere, disturbances can propagate as waves, Rossby waves, named after the meteorologist who first described them. These waves travel around the planet, and under certain conditions they can interfere with each other, creating standing wave patterns that don't move. When multiple waves with the right wavelengths interfere, they can create polygonal patterns, triangles, squares, hexagons, depending on the number of waves and how they align. On Saturn, the conditions happen to favour a hexagon. 6 waves fitting perfectly around the latitude where the jet stream flows, their peaks and troughs defining the corners and sides of the hexagonal structure. The wind speed differential between the jet stream and surrounding air maintains the pattern, preventing it from blurring out. It's elegant physics, emerging from equations that describe fluid flow on rotating spheres, manifesting as a visible structure larger than Earth. The mathematics predicted that such patterns were possible long before we saw one in nature. Saturn provides the laboratory, the demonstration that these theoretical possibilities are real, that under the right conditions rotating fluids naturally organize themselves into geometric shapes that look designed but emerge purely from physical law. Saturn's south pole had a massive hurricane-like vortex with a distinctive eye similar to Earth's hurricanes. Unlike Earth's storms, this one persisted for years without weakening or moving, and Cassini observed it throughout its mission, documenting a storm system that would be catastrophic on Earth, but is apparently normal for Saturn, a permanent feature anchored to the pole, spinning continuously, fed by energy from Saturn's interior heat. The eye was clearly defined in infrared images, a warm spot at the centre where descending air compressed and heated, surrounded by towering clouds rising tens of miles high, winds screaming around the perimeter. It looked like a hurricane, functioned like a hurricane, but existed in an environment where hurricanes don't need ocean heat to sustain them. Saturn's internal heat provides constant energy, allowing the storm to persist indefinitely. Earth's hurricanes are transient. They form over warm ocean water, derive their energy from evaporation and latent heat release, and die when they hit land or move over cold water. Saturn's pole storm doesn't have those limitations. It's not going anywhere. It's locked to the pole by the Coriolis effect and planetary rotation. It's not going to run out of energy. Saturn's interior will keep producing heat for billions of years. It's a permanent fixture, a storm that might have been raging since before humans existed and might continue long after we're gone. The South Pole storm had an eye 1,250 miles across, about 50 times larger than typical hurricane eyes on Earth. Winds in the wall surrounding the eye reached 350 miles per hour. Earth's strongest hurricanes, Category 5 storms, have winds around 160 miles per hour. Saturn's pole storm has sustained winds more than twice that fast, swirling around an eye large enough to swallow multiple Earths. Inside the eye, conditions would be relatively calm, just as in Earth's hurricanes. The descending air would clear clouds, creating a region where you could potentially see deeper into Saturn's atmosphere, down to warmer layers that glow in infrared. Around the perimeter, the eye wall, where the strongest winds occur, would be chaos, updrafts and downdrafts, clouds rising and falling, lightning flickering, a maelstrom of energy and motion. Cassini imaged the eye in remarkable detail, showing structure within structure, smaller vortices orbiting around the main eye, cloud features appearing and disappearing, the eye itself wobbling slightly as the storm evolved. It was mesmerizing to watch, this enormous storm on another world, be playing out according to the same basic physics that governs Earth's weather, but on a scale and with an intensity that makes our most powerful hurricanes seem gentle by comparison. Lightning on Saturn is about 10,000 times more powerful than lightning on Earth. These mega bolts illuminate clouds hundreds of miles across, visible from space. Cassini detected them both optically, as bright flashes in the clouds, and as radio emissions, the crackle of electrical discharge powerful enough to radiate across the electromagnetic spectrum. On Earth, lightning occurs in thunderstorms, in cumulonimbus clouds where updrafts and downdrafts separate electrical charge, building up voltage differences until the air breaks down and current flows. The same process happens on Saturn, but the scale is different. Saturn's storms are larger, more energetic, are driven by stronger convection from the planet's internal heat. The charge separation is greater, the voltage difference is larger, the resulting discharge is more powerful. A single lightning bolt on Saturn can release as much energy as hundreds of terrestrial bolts. The flash illuminates not just one cloud, but entire storm systems, revealing structure that's otherwise hidden. The radio emission is so strong that it can be detected from Earth during major storm outbreaks, a reminder that Saturn's weather is violent, energetic, powerful enough to announce itself across the solar system. Saturn's lightning storms can last for months, disappearing and reappearing in predictable patterns. They're nicknamed Great White Spots when they grow large enough to see from Earth. These aren't small, localized thunderstorms. They're planet-spanning eruptions, bright regions thousands of miles across where clouds boil upward, lightning flashes constantly, and material from deep in Saturn's atmosphere is dredged up and exposed to sunlight. Great white spots appear irregularly, roughly once per Saturn year, once every 29 Earth years, though the timing isn't exact. They tend to occur during Northern Hemisphere summer, suggesting a seasonal trigger, possibly related to temperature differences between equator and pole or changes in atmospheric circulation. When they appear, they're dramatic, bright enough to see through amateur telescopes from Earth, distinctive enough that their appearance makes news in astronomy circles. Cassini observed a great white spot in 2010 to 2011, tracking it for months as it evolved, spread around Saturn's circumference, eventually encircling the entire planet in a turbulent band. The storm injected material into the upper atmosphere, changed cloud compositions, created disturbances that persisted long after the lightning stopped. And then it faded, dissipated, leaving Saturn looking much as it had before, waiting for the next eruption decades in the future. Cassini detected enormous electrical storms on Saturn that generated radio emissions audible as static. Scientists could literally hear Saturn's weather through radio telescopes. The spacecraft carried a radio and plasma wave instrument designed to detect electromagnetic radiation at radio frequencies, and when lightning flashed in Saturn's atmosphere, the instrument picked up the signal, bursts of static, crackling noise, the electromagnetic signature of electrical discharge. These radio emissions are called Saturn electrostatic discharges, or SEDs, and they're distinctive. Unlike the continuous hiss of background radiation, or the steady tones from other astronomical sources, SEDs are impulsive, intermittent, clustered during storm events. When a major storm system was active, Cassini would detect hundreds or thousands of SEDs per hour, creating an almost constant crackle in the radio receivers. Engineers converted these signals to audio frequencies so humans could hear them. The result sounds like static on an old radio, or the crackle of a Geiger counter, or distant popcorn popping. Impulsive bursts separated by silence, clustering during active periods, fading when storms quieted. It's an odd thing to realize. Saturn makes sounds, or at least produces electromagnetic waves that we can convert to sounds. And for 13 years Cassini listened, recording Saturn's electrical heartbeat, documenting when and where lightning struck, mapping storm systems through their radio signatures. Saturn's moon Rhea may have once had its own ring system, making it a moon with rings around a planet with rings. If true, it would be rings within rings, a cosmic nesting doll of gravitational architecture. The evidence is tentative. Subtle features in Cassini's magnetometer data that suggested charged particles were being absorbed by something orbiting Rhea, possibly debris in a disk or ring configuration. Imagine it. Rhea, a moon 950 miles across, orbiting Saturn, itself surrounded by narrow rings of dust and ice. As you approached Rhea, you'd see Saturn and its magnificent rings in the sky, and closer, Rhea itself wearing its own smaller crown. Rings around a moon, around a ringed planet, around a star. Nested structures, each level of gravity creating its own disk, its own orbital system. The evidence hasn't been confirmed, though. Later observations didn't clearly detect rings, and it's possible the magnetometer signature was caused by something else. An atmosphere, or charged particles trapped in Rhea's weak magnetic field, or measurement artifacts. Rhea might have had rings in the past that have since dissipated, or might never have had them at all. The question remains open, tantalizing, a reminder that even after intensive study, Saturn and its moons still hold surprises, still offer possibilities we haven't fully explored. Many of Saturn's moons are tidally locked, always showing the same face toward the planet. Like Earth's moon, they rotate once per orbit, frozen in eternal vigilance. This happens because of tidal forces, the same forces that create ocean tides on Earth, that heat Enceladus's interior, that maintain the Roche limit. When a moon orbits close enough to its planet, the planet's gravity pulls slightly stronger on the near side than the far side, creating a torque that acts to align the moon's longest axis toward the planet. Over millions of years, this torque slows the moon's rotation, gradually synchronizing it with the orbital period until the moon is locked. One face always toward the planet, the other always facing away. It's the minimum energy configuration, the stable equilibrium toward which tidal forces drive all sufficiently close moons. Our moon is tidally locked to Earth. That's why we always see the same lunar face. Why there's a dark side we never see from Earth's surface. Saturn's inner and mid-sized moons are all tidally locked. Mimas, Enceladus, Tethys, Dione, Rhea, Titan all show the same hemisphere to Saturn throughout their orbits. Only the distant irregular moons, captured asteroids in eccentric orbits, tumble freely, too far away for tidal forces to have locked them yet. On the surface of a tidally locked moon, Saturn would hang motionless in the sky, always in the same position, never rising or setting, a permanent fixture marking the division between the hemisphere that sees it and the hemisphere that never does. Tidal forces from Saturn flex Enceladus's interior, generating heat that melts ice into subsurface oceans. Gravity's gentle squeeze becomes warmth, creating habitable conditions in unlikely places. The process is called tidal heating, and it works because Enceladus's orbit isn't perfectly circular. It's slightly elliptical, which means the distance between Enceladus and Saturn changes over each orbit. When Enceladus is closer to Saturn, tidal forces are stronger. The moon gets stretched slightly in Saturn's direction. When it's farther away, the forces weaken and the moon relaxes back toward a more spherical shape. This constant flexing, squeezing and relaxing twice per orbit generates friction in Enceladus's interior. Ice crystals rub against each other, rock grinds against rock, and friction converts mechanical energy into heat. Over millions of years, this heat accumulates, melts ice, creates and maintains the subsurface ocean we infer from the geysers and from Cassini's gravitational measurements. Without tidal heating, Enceladus would be frozen solid, dead, inactive. But Saturn's gravity keeps it alive, keeps it warm enough for liquid water to exist, possibly warm enough for life. It's a partnership between moon and planet, between orbit and geology, creating conditions that wouldn't exist if Enceladus orbited alone through space. Saturn's moon. Dione might also have a subsurface ocean, detected through subtle wobbles in its rotation. Several of Saturn's moons may hide secret oceans beneath their frozen exteriors. Dione is larger than Enceladus, about 700 miles across, and shows no obvious signs of geological activity like geysers or fresh ice. But Cassini measured how Dione wobbles as it orbits Saturn, and the wobble is larger than expected for a completely solid moon. The wobble works like this. If Dione were solid all the way through, its outer ice shell would be rigidly connected to its rocky interior, and the whole moon would rotate as a single unit. The wobble would be small, predictable, determined by Dione's shape and mass distribution. But if there's a liquid layer between the ice shell and the rocky core, the shell can move independently, sliding slightly relative to the interior, creating a larger wobble. The measured wobble suggests liquid, probably a subsurface ocean tens of miles deep, warmer than the ice above and below, possibly heated by tidal forces similar to Enceladus, though less intensely. Dione doesn't advertise its ocean the way Enceladus does. There are no geysers, no obvious signs of activity, but beneath the surface there might be water, quietly existing, possibly harbouring chemistry we can't yet detect, another hidden ocean in Saturn's system of moons. Phoebe, one of Saturn's outer moons, orbits backward compared to most other moons. It's likely a captured object from the outer solar system, a refugee from distant regions. Most of Saturn's moons orbit in the same direction Saturn rotates, counterclockwise as viewed from above Saturn's north pole. This is expected. They formed from the same disk of material that surrounded Saturn during its formation, inheriting that disk's rotation. But Phoebe orbits clockwise, backward, retrograde. Its orbit is also highly inclined, tilted about 175 degrees relative to Saturn's equator, and eccentric, elongated rather than circular. All these characteristics suggest Phoebe wasn't born in Saturn's system. It formed elsewhere, though probably in the Kuiper belt far beyond Neptune, and was captured by Saturn's gravity when it wandered too close. Phoebe's composition supports this idea. It's darker than Saturn's inner moons, rich in organic compounds and carbon, similar in many ways to Kuiper belt objects and to Pluto. It's like a sample from the outer solar system, transplanted to Saturn's orbital space, forever orbiting a planet that isn't its birthplace. Cassini flew close to Phoebe in 2004, imaging its battered, cratered surface, documenting its composition, confirming that it's an outsider, a wanderer that found a permanent home in Saturn's gravitational embrace. Phoebe might be a captured Kuiper belt object, similar to Pluto but much smaller. Saturn's gravity snatched it from the outer darkness, making it a permanent captive. The Kuiper Belt is the region beyond Neptune where small icy bodies orbit, leftovers from the solar system's formation, never incorporated into planets, preserved in a frozen state for billions of years. Pluto is the most famous Kuiper Belt object, but there are thousands of others, ranging from Pluto-sized down to tiny fragments. Phoebe is small by Kuiper Belt standards, only about 130 miles across, irregular in shape, too small to pull itself into a sphere. But it shares many characteristics with its distant cousins. The dark surface rich in organics, the density suggesting a mix of rock and ice, the composition similar to comets and other primitive solar system bodies. If Phoebe formed in the Kuiper Belt, it spent billions of years in the outer solar system before something perturbed its orbit, maybe a close encounter with Neptune, and maybe gravitational interactions with other Kuiper Belt objects, and sent it sunward. At some point, Phoebe's new orbit crossed Saturn's orbital path, and Saturn's gravity captured it, pulling it into orbit, making it a moon. Now, Phoebe orbits Saturn every 550 days, a long looping path far from the planet, observing Saturn and its other moons from a distance, an outsider among a family of siblings, forever marked by its different origin. Saturn's moon Janus and Epimetheus share nearly identical orbits and swap positions every few years. When they approach each other, gravity causes them to trade orbital paths in an elegant dance. This orbital swap is unique in the known solar system. Janus and Epimetheus orbit Saturn at nearly the same distance. Their orbital radii differ by only about 30 miles, less than the diameter of either moon. Here's how the swap works. At any given time, one moon orbits slightly closer to Saturn than the other. The inner moon travels faster. Objects in lower orbits always move faster due to stronger gravitational pull, so gradually the inner moon catches up to the outer one. When they get close, within a few thousand miles, their mutual gravitational attraction becomes significant. The inner moon, being closer to the outer one, gets pulled slightly outward, gaining energy, rising to a higher orbit. The outer moon gets pulled slightly inward, losing energy, dropping to a lower orbit. They swap positions. The formerly inner moon is now outer, travelling slower. The formerly outer moon is now inner, travelling faster. They drift apart and the cycle repeats every 4 years. It's a gravitational waltz, perfectly choreographed by physics, playing out in slow motion over years. No other moons do this. Janus and Epimetheus are special, locked in this unique configuration, probably the result of both moons forming from the breakup of a single larger moon in the distant past. Their siblings, sharing an orbit, taking turns being inner and outer, dancing through space in a way that seems almost intentional, but emerges purely from the mathematics of gravity and motion. Some of Saturn's smaller moons are probably fragments from larger moons shattered by impacts. They orbit in groups, cosmic siblings born from ancient catastrophes. We can identify these families by their orbital characteristics. Moons that share similar orbital radii, inclinations and eccentricities probably came from the same parent body, broken apart by collision, now orbiting as a cluster of fragments. The impacts that created these families must have been violent. A collision energetic enough to shatter a moon doesn't just crack it, it explodes it, sending fragments flying in all directions, some escaping entirely, others falling back together or entering orbits near the impact site. The fragments we see today are survivors, pieces large enough to remain coherent, orbiting as separate bodies but still gravitationally associated with their siblings. Over time, these fragment families can evolve. Smaller pieces get swept up by larger ones through gentle collisions. Gravitational interactions with Saturn or other moons can scatter the family, changing orbital parameters, dispersing members. But the signatures remain, visible in orbital data telling stories of ancient violence, of moons that once existed but were destroyed, leaving only pieces behind. Saturn's rings probably formed relatively recently because bright, pure ice doesn't stay clean for billions of years. Cosmic dust would have darkened ancient rings, but Saturn's remain brilliantly white. Every year, meteorites hit the rings, tiny fragments of asteroids and comets, dust grains travelling at high velocities, colliding with ring particles and adding their material to the rings. Most meteorites contain rock and carbonaceous material, dark stuff, significantly darker than water ice. When these meteorites hit ring particles, they deposit a thin layer of dark material on the ice surface. Over time, this contamination accumulates. Calculations suggest that if the rings were billions of years old, they should have accumulated enough meteoritic material to darken significantly, yet reducing their brightness by a noticeable amount. But Saturn's rings remain bright, almost as bright as fresh snow, reflecting about 60 to 70% of incident sunlight. This brightness suggests they haven't been around long enough to accumulate substantial contamination, supporting the idea that they're young, maybe only 100 to 400 million years old. There are caveats. Maybe there's a cleaning process we don't understand. Maybe small particles shed contaminated surfaces preferentially. Maybe the contamination rate is lower than we think. But the simplest explanation is youth. The rings are bright because they're relatively new, recent additions to Saturn's system, temporary decorations that won't last forever. The rings are being contaminated by micrometeorite impacts at a measurable rate. These scientists use this darkening rate to estimate the ring's age, like reading cosmic tree rings. The process works through spectroscopy, analysing the light reflected from the rings to determine their composition and colour. Over the years of Cassini's mission, scientists could measure subtle changes in the ring's reflectivity, tracking how contamination accumulated, calculating the rate at which the rings were darkening. It's a slow process, imperceptible on human timescales. You can't watch the rings darken from year to year. The changes are too subtle. But over decades, with precise instruments, the trend becomes measurable, and once you know the darkening rate, you can extrapolate backward. If the rings are darkening this fast now and they're this bright currently, how long have they been accumulating contamination? The math points toward ages measured in hundreds of millions of years, not billions. It's forensic astronomy, using current processes to deduce past history, reading the evidence written in reflected light. The rings carry their age in their brightness, their youth evident in their purity. Every micrometeorite impact adds another microscopic layer to that record, another tiny increment of darkening, another data point in the story of how long Saturn has worn its crown. Ring rain falls onto Saturn at a rate of about 2,000 pounds per second. The rings are literally dissolving, pulled down by Saturn's magnetic field and gravity. 2,000 pounds per second sounds like a lot, and in human terms it is. That's roughly the weight of a small car falling into Saturn every second. But compared to the total mass of the rings, it's tiny. A gradual erosion that takes millions of years to make a noticeable difference. The rain happens because ring particles become electrically charged through interactions with ultraviolet light and Saturn's magnetosphere. Once charged, they respond to Saturn's magnetic field, which guides them along field lines toward the planet's poles. The particles spiral downward, entering Saturn's upper atmosphere, vaporizing from friction, depositing water molecules into the gas surrounding the planet. Scientists detected this ring rain by observing spectral signatures of water in Saturn's upper atmosphere at latitudes where water shouldn't exist, based on Saturn's internal composition. The water is coming from above, from the rings, raining down at steady rate, adding a faint shimmer of water molecules to Saturn's stratosphere. It's been happening for as long as the rings have existed, and it will continue until the rings are gone, a slow transfer of mass from ring to planet, from ice orbiting in space to vapor mixed into atmosphere. At the current rate of ring rain, Saturn's entire ring system could disappear in 100 million years. We're living in a brief cosmic moment when Saturn wears its crown of ice. 100 million years sounds like a long time, and it is. Longer than the age of the dinosaurs' extinction, longer than mammals have dominated Earth. But in cosmic terms, it's brief. Saturn is 4.5 billion years old. 100 million years is only about 2% of Saturn's total lifetime. If the rings formed recently, say 300 million years ago, then they'll have existed for a total of 400 million years before disappearing, less than 10% of Saturn's history. Yet for most of its existence, Saturn was ringless, and after the rings are gone, it will be ringless again, returning to its original state, just a large gas giant without distinguishing features. Future civilizations, if any exist, might look at Saturn and see nothing special. They might study it, measure it, catalogue it as a gas giant similar to Jupiter but smaller. If they discovered historical records from our era, images, descriptions, observations, they'd initially doubt them. Rings? Around Saturn? Are you sure? They might think we exaggerated, that we prettified our images, that we saw what we wanted to see, but we're not imagining them. The rings are real, spectacular and temporary. We're lucky to live when we do, in the narrow window when Saturn has its most iconic feature. The Cassini mission ended by diving into Saturn's atmosphere to avoid contaminating potentially habitable moons. Even in death, the spacecraft protected the worlds it had spent years studying. By September 2017, Cassini was running low on fuel. Without fuel for maneuvering, it couldn't maintain a stable orbit, and eventually it would crash into something, maybe Titan, maybe Enceladus, maybe another moon. That was unacceptable. Cassini, built on Earth, carried Earth microbes despite sterilization procedures. If it crashed onto Enceladus or Titan, moons that might harbor conditions suitable for life, those microbes might contaminate the environment, potentially compromising future searches for a native life. The only way to guarantee no contamination was to ensure Cassini never touched those moons. So mission controllers commanded Cassini to dive into Saturn itself. On September 15, 2017, the spacecraft made its final plunge, entering Saturn's atmosphere at high speed, transmitting data until the very end, then burning up like a meteor, its atoms mixing with Saturn's gases, becoming part of the planet it had studied. It was a deliberate sacrifice, a final act of scientific responsibility. Cassini chose oblivion over the risk of contamination, protecting the worlds it loved from the one thing it couldn't control, itself. Cassini discovered that Titan's surface lakes are filled with ultra-pure liquid methane and ethane. These alien seas are clearer than Earth's purest water, transparent and pristine. On Earth, lakes contain dissolved minerals, suspended sediments, organic particles, algae, mere pollution. all sorts of contaminants that reduce clarity. Even the clearest mountain lakes contain some impurities. But Titan's lakes are different. Liquid methane and ethane are excellent solvents for some compounds, but not for others. The minerals and salts that dissolve readily in water don't dissolve in hydrocarbons. The result is liquid that's chemically pure, free from dissolved solids, extraordinarily clear. If you could stand on the shore of Ligeia Mare, one of Titan's northern seas, and look into the liquid, you'd see down through meters of methane, the bottom clearly visible if shallow enough, the liquid so transparent it barely distorts the view. Of course, the liquid would be frigid, about minus 290 degrees Fahrenheit, cold enough to freeze you instantly. And it wouldn't be colourless. Liquid methane has a slight blue tint, while ethane is clearer. And mixed together in Titan's lakes, they'd create a pale blue-green liquid, shimmering under Titan's hazy orange sky, lapping gently against shores of water ice as hard as granite. An alien ocean on an alien world, beautiful in ways that have nothing to do with earthly aesthetics. Titan's atmosphere is 50% thicker than Earth's, creating surface pressure similar to being 15 feet underwater. Despite the cold, you could walk on Titan without a pressure suit, just extreme insulation. Earth's atmospheric pressure at sea level is about 14.7 pounds per square inch. Titan's surface pressure is about 21.5 pounds per square inch. Half, again as high, comparable to the pressure you'd experience swimming about 15 feet below the surface of Earth's ocean. This thick atmosphere has consequences. It creates drag that slows falling objects, making parachute landings easy. The Huygens probe that landed on Titan in 2005 descended slowly under parachutes, gently touching down after hours of descent. It scatters light, creating the orange haze that obscures the surface. It supports weather systems, allows for rain and clouds and wind, and it means that pressure isn't the limiting factor for human exploration. If you visited Titan, you'd need insulation, a heated suit to prevent the minus 290 degrees Fahrenheit temperature from freezing you solid. You'd need oxygen to breathe. Titan's atmosphere is nitrogen and methane, not breathable. But you wouldn't need a pressure suit. You could wear something more like an insulated diving suit than a space suit, flexible enough to move naturally, robust enough to keep you warm but not rigid, not fighting against pressure differential. Titan is hostile. The end, but in a different way than the Moon or Mars. The challenges are different, the solutions different, the experience of being there different from anywhere else humans might eventually explore. Complex organic molecules, the building blocks of life, rain from Titan's atmosphere like snow. Chemistry that took millions of years on Earth happens continuously in Titan's alien sky. In Titan's upper atmosphere, ultraviolet light from the sun breaks apart methane molecules, creating reactive fragments that recombine into more complex compounds. These include tholins, reddish-brown organic compounds that give Titan its orange colour, and various hydrocarbons, nitriles, and other carbon-rich molecules. These molecules drift downward, settling onto Titan's surface like a slow, perpetual snowfall of organic chemistry. Over billions of years, they've accumulated, creating deposits that might be meters thick in places, layers of organic material covering Titan's icy landscape. Some of this material washes into the lakes, dissolves or settles to the bottom, participates in further chemical reactions. Some remains on the surface, coating the ice, filling low spots, creating the dark equatorial dunes that Cassini observed. It's prebiotic chemistry, not life, but the chemical steps that might lead toward life under the right conditions. On Earth, similar chemistry occurred in the atmosphere and oceans billions of years ago, eventually leading to the first self-replicating molecules, the first metabolism, the first life. Titan might be running a similar experiment, though slower, colder, proceeding through different pathways. We don't know where it will lead, if anywhere. But the raw materials are there, the chemistry is active and time is abundant. Titan is a laboratory conducting experiments in organic chemistry on a planetary scale, patiently assembling complexity from simpler components. Titan's lakes evaporate and refill seasonally, creating bathtub rings of organic residue. These rings mark ancient shorelines, showing how liquid levels change across decades. Just like a bathtub that's been drained leaves a ring of soap scum at the old waterline, Titan's lakes leave rings of organic material at previous lake levels. As methane evaporates, dissolved organics precipitate out, coating the shoreline rocks, water ice, on Titan, with a dark layer. Cassini observed these rings in radar images, bright bands around some lakes indicating where shorelines once were. They're evidence that Titan's lake levels change significantly over time, possibly over seasonal cycles. During Titan's long summer, 7 Earth years, evaporation might exceed rainfall, causing lake levels to drop, exposing shorelines that were previously submerged. During winter, the balance reverses, rainfall exceeds evaporation. Lakes refill, submerging the rings again. The rings are a record, a way of reading Titan's climatic history from orbital images. Each ring represents a stable lake level that persisted long enough to deposit a visible layer of organics. Multiple rings suggest multiple stable levels, possibly corresponding to different seasons or climate cycles. It's stratigraphy, reading history from layers, but instead of rock layers on Earth, it's organic deposits on an icy moon. Dayast, recording fluctuations in liquid methane levels across decades or centuries. We've never seen Titan's North Pole lakes completely full. They're still filling from recent summer rains. Seasonal changes on Titan unfold over decades, requiring patience to observe complete cycles. When Cassini arrived in 2004, it was winter in Titan's northern hemisphere. The North Pole was dark, cloud-covered, and radar images showed the lakes were relatively empty, depleted from years of northern winter. As Titan progressed toward northern spring and summer, clouds formed over the North Pole, rainfall increased, and the lakes began to fill. Cassini watched this happen over 13 years, documenting the gradual rise in lake levels, the appearance of new smaller lakes, the connection of previously separate bodies of liquid. But Cassini's mission ended in 2017 before northern summer was complete, before the lakes reached their maximum fill. We missed it. We don't know how full Titan's lakes get at peak summer, how much liquid they contain when fully filled, whether they overflow and create new drainage patterns. That data will have to wait for future missions, for spacecraft that can observe Titan over complete seasonal cycles, documenting not just a portion of the change, but the full extent of Titan's hydrological variations. It's frustrating, but it's also a reminder of the timescales involved. Titan's seasons are long. Observing them completely requires decades of patience, commitment that extends beyond single missions. Saturn's moon Mimas creates the largest gap in the rings, the Cassini division, through orbital resonance. Jussi, Every particle in that gap is nudged by Mimas's gravity, swept clean over millions of years. The Cassini division is about 3,000 miles wide, a prominent dark band separating the A ring from the B ring, visible even through small telescopes from Earth. It looks empty, though it's not completely devoid of particles, just much less dense than the bright rings on either side. The gap exists because of Mimas, which orbits Saturn farther out than the rings. Any particle orbiting in the Cassini division completes exactly 2 orbits for every 1 orbit of Mimas. This 2-to-1 resonance means the particle and Mimas return to the same relative positions repeatedly, and each time Mimas's gravity tugs on the particle, always in a similar direction, the nudges accumulating over time. Gradually, these repeated nudges change the particle's orbit, by pushing it either inward or outward, clearing it out of the resonance zone. Over millions of years, this process has swept the Cassini division largely clean, creating the gap we observe. It's a demonstration of resonance at work, of how small, repeated gravitational influences can produce large-scale structures, shaping the rings into the complex pattern of bands and gaps that make Saturn's ring system so intricate. Orbital resonances throughout Saturn's rings create hundreds of gaps, waves, and density variations. The ring system is a symphony of gravitational music, each moon playing its part. Beyond the Cassini division, there are dozens of smaller gaps: the Encke gap, the Keeler gap, the Huygens gap, each carved by resonances with different moons or by small moonlets embedded in the rings themselves. And it's not just gaps. Resonances also create density waves, spiral patterns that propagate through the rings like ripples in water, except they're made of orbiting ice particles responding to periodic gravitational tugs. These waves are visible in detailed images as alternating bright and dark bands spiraling outward from resonance locations, beautiful geometric patterns etched into the rings by invisible forces. Each resonance has a signature, a characteristic pattern determined by which moon creates it, and what type of resonance it is. Scientists can read the rings like sheet music, identifying which features correspond to which moons, understanding how the gravitational relationships between Saturn, its rings, and its moons create the structures we observe. It's all connected. Every moon influences the rings, every resonance leaves its mark. The whole system coupled through gravity into a complex evolving arrangement that's been playing out for as long as the rings have existed. Saturn's rings may have inspired the concept of Dyson spheres, artificial structures surrounding stars. Nature created a disk around a planet. Perhaps advanced civilizations could do similar things with stars. The idea of a Dyson sphere was proposed by physicist Freeman Dyson in 1960 as a thought experiment about how advanced civilizations might harness stellar energy by surrounding their star with a shell or swarm of solar collectors. Dyson himself noted that Saturn's rings were an example of matter arranged in a disk around a central body, demonstrating that such configurations were stable and possible. Of course, Saturn's rings are nothing like a Dyson sphere. They're ice, not solar panels. They orbit passively rather than collecting energy. They're thin rather than fully enclosing. But they prove the principle. You can have vast amounts of material orbiting a central body in a stable configuration. The analogy is loose, but it's there. Nature creates rings around planets. Could intelligence create rings or spheres or swarms around stars? The physics allows it. The engineering challenges are immense but not impossible in principle. Saturn's rings exist because gravity and collisions arranged ice into a disk. Dyson spheres, if they exist anywhere in the universe, would exist because intelligence arranged matter to capture starlight. Different processes, similar geometry, both emerging from the same fundamental laws. The total mass of Saturn is 95 times greater than Earth's, yet it spins nearly 2.5 times faster. This rapid spin bulges its equator, making Saturn visibly flattened even in small telescopes. Earth rotates once every 24 hours. Saturn rotates once every 10.7 hours, less than half the time despite being vastly larger. That rapid rotation creates enormous centrifugal force at Saturn's equator, pushing outward, counteracting gravity, making the planet wider at its middle than from pole to pole. The difference is noticeable. Saturn's equatorial diameter is about 75,000 miles, but pole to pole it's about 68,000 miles, a difference of roughly 10%. If you photographed Saturn, you could see that it's not quite spherical, that it's squashed, flattened, oblate. No other planet in the solar system shows this effect as dramatically. Jupiter is also oblate, but less so. Earth has a slight bulge, imperceptible without precise measurements. Saturn's oblateness is tied to its low density and rapid rotation. The planet's material isn't strongly bound by gravity, it's mostly gas, easily deformed by rotational forces. The combination creates visible flattening, a shape that reflects the balance between gravity pulling inward and rotation pushing outward. Saturn is a spinning ball of gas trying to fly apart, held together by its own mass, caught in equilibrium between collapse and dispersal. Saturn's equatorial diameter is about 75,000 miles, but pole to pole it's 10% shorter due to centrifugal force. It's not quite a sphere, more like a slightly squashed ball spinning in the cosmic dark. This flattening affects everything about Saturn: its gravitational field, its internal structure, how material is distributed between equator and poles, how the atmosphere circulates. Thus, near the equator, material experiences less effective gravity because centrifugal force partially counteracts gravitational pull. Near the poles, there's no centrifugal force, only gravity pulling directly towards Saturn's center. This creates pressure differences, temperature gradients, circulation patterns that wouldn't exist on a non-rotating or slowly rotating planet. The flattening shapes the weather, influences the jet streams, contributes to the formation of features like the hexagon, and the flattening itself changes over time, though imperceptibly. As Saturn slowly contracts, cooling, shrinking, losing heat to space, its rotation rate changes, and with it, the degree of flattening. Billions of years ago, Saturn was slightly less flattened. Billions of years from now, it will be slightly more spherical. The changes are tiny, as is measurable only through precise observations across centuries, but they're real, evidence that Saturn isn't static, that it's evolving, aging, gradually transforming even as it appears unchanging. We still don't know exactly how long a day is on Saturn. Measurements vary by several minutes. Without a solid surface, measuring rotation becomes strangely difficult, even uncertain. On Earth, we can measure rotation by watching a mountain or coastline return to the same position. On Saturn, there are no mountains, no coastlines, no fixed reference points. The clouds move at different speeds than the interior. Different atmospheric layers rotate at different rates. There's nothing solid to watch. Scientists have tried multiple methods. They've tracked cloud features, but clouds move with the wind, not with Saturn's rotation. They've measured radio emissions from Saturn's magnetosphere, which is generated in the interior and should rotate with the planet, but even those measurements show variations, suggesting the magnetosphere doesn't rotate uniformly, or that there are secondary effects complicating the signal. The current best estimate for Saturn's rotation period is about 10 hours, 33 minutes, but with uncertainty of several minutes either way. Different measurement techniques give slightly different results, and we're not entirely sure which is correct, or if the question even has a single answer. Saturn might not have one rotation period, but several, depending on which layer you're measuring. It's a reminder that even basic questions, how long is a day, can be surprisingly hard to answer for planets that don't have solid surfaces. Radio emissions from Saturn's interior provide the best estimate of its rotation period. We listen to the planet's electromagnetic heartbeat to understand its deepest rhythms. Saturn's magnetic field is generated deep inside, in the metallic hydrogen layer where convection currents and rotation combine to create a dynamo. That magnetic field rotates with the interior, and as it rotates, it produces radio emissions, electromagnetic waves that pulse with a regular period. Cassini detected these emissions throughout its mission, recording the rhythm, the timing, the subtle variations. The period isn't perfectly constant. It changes slightly over years, suggesting that the interior rotation isn't perfectly uniform, that there are currents, circulation patterns, complexities we don't fully understand. But averaged over long periods, the radio emissions provide the best window we have into Saturn's interior rotation, the only way to measure something we can't see directly. It's like listening to a heartbeat to understand what's happening inside a body. We can't open Saturn up, can't probe its interior directly, can't measure rotation through visual observation, but we can listen, detect the electromagnetic signals, analyze their timing, infer from those signals what must be happening thousands of miles below the visible clouds. Saturn speaks, if you know how to listen, broadcasting its rotation in radio waves, patient and constant, waiting for anyone with the right instruments to hear. Despite decades of study, Saturn continues to surprise us, a reminder that mystery persists even in familiar places. The ringed giant we've known since childhood still holds secrets, lay patiently waiting to be discovered. We've sent 4 spacecraft to Saturn: Pioneer 11, Voyager 1, Voyager 2, and Cassini. We've observed it through telescopes for over 400 years. We've analysed its light, measured its mass, mapped its moons, documented its rings in exquisite detail. And yet, questions remain. How old are the rings really? Does Titan harbour life in its subsurface ocean? What maintains the hexagon? Why does Saturn's magnetic field align so perfectly with its rotation axis, unlike every other planet? What's happening in Saturn's interior at pressures and temperatures we can't replicate in laboratories? How do the seasonal variations in the rings work? What happens to ring rain when it enters Saturn's atmosphere? Some of these questions will be answered by future missions. Yet some might remain unanswered for decades or centuries, waiting for technology that doesn't exist yet, for observations that require instruments we haven't imagined. And some might never be answered, might remain permanently mysterious, beyond our ability to observe or understand. Saturn is generous with its wonders, but stingy with its explanations. It shows us beauty, but withholds understanding. It invites curiosity, but doesn't promise resolution. Saturn orbits the Sun at a distance of about 890 million miles, nearly 10 times farther than Earth. At that distance, the Sun appears about 1/10 the size it does from Earth, and provides about 1/100th the warmth. If you could stand on a platform in Saturn's upper atmosphere, suspended somehow above the clouds, and is protected from the cold and pressure, the Sun would look like a very bright star, still far brighter than anything else in the sky, but small, distant, less commanding than the enormous golden disk we see from Earth. The reduced sunlight has profound effects. Saturn receives very little solar heating compared to inner planets. Most of its warmth comes from its own interior, from gravitational contraction and helium rain. The low sunlight makes temperatures frigid, creates the chemical environment where methane can rain on Titan, allows water ice to be as hard as rock on the moons. Distance shapes everything: the temperature, the chemistry, the atmosphere, the seasons. And yet Saturn orbits the same star we do, follows the same laws, responds to the same gravitational influences. It's part of our solar system, our cosmic neighborhood, connected to Earth through shared origin and ongoing gravitational relationships. We're in a system, warm, close to the Sun. Saturn is outer system, cold, distant, but we orbit the same center, emerge from the same cloud of gas and dust billions of years ago, siblings separated by distance but not by kinship. Saturn's influence extends far beyond its visible form. Its magnetosphere, the bubble carved in the solar wind by its magnetic field, extends millions of miles, encompassing the orbits of many moons, creating an environment unique in the solar system. Inside this magnetosphere, Saturn's magnetic field dominates. Charged particles from the Sun, from the rings, from moon geysers, all get trapped, guided along field lines, accelerated to high energies. The magnetosphere protects the inner moons from the solar wind. This creates radiation belts where particles accumulate, influences atmospheric chemistry through particle bombardment. It's an invisible structure, detectable only through its effects, but it's vast, powerful, constantly interacting with everything in Saturn's orbital space. Without it, the rings would be different, more affected by solar wind, possibly dispersing faster. The moons would be different, more radiation, different chemistry, possibly different geological processes. Saturn is more than just a planet. It's the center of an entire system, gravitational, magnetic, chemical, that extends across millions of miles, encompasses dozens of moons, includes some of the most interesting environments in the solar system. Understanding Saturn means understanding all of it, the planet and its influence, the visible and invisible, the solid moons and the tenuous magnetosphere, all interconnected, all part of the same cosmic family. And so we come to the end of our journey through Saturn's realm, though the journey itself is never truly complete. Saturn will continue orbiting the Sun long after we've finished talking about it, its rings slowly raining down, its moons continuing their ancient dances, its storms raging in the dark, its secrets waiting patiently for the next spacecraft, the next observation, the next curious mind to ask one more question. Perhaps that's the most important thing to remember about Saturn. Not any particular fact, not the measurements or numbers or names, but the simple truth that it exists. A giant world wrapped in ice surrounded by moons, so far away that light takes over an hour to travel from there to here, yet close enough that we can study it, photograph it, send machines to orbit it and sample its moons. Saturn is real, not a myth, Not an artist's rendering, not a symbol. A planet made of matter, governed by physics, beautiful without intention, complex without design. We've explored 100 facts tonight, but there are thousands more, millions more, an infinite number of perspectives as details and relationships that could be examined. Saturn is inexhaustible. We could spend lifetimes studying it and still find new questions, new mysteries, new wonders hiding in the data. And that's fitting somehow. The universe should be bigger than our understanding, should always offer one more question, one more discovery, one more reason to look up at the sky and feel that mixture of knowledge and mystery that makes science both satisfying and endlessly compelling. Saturn teaches patience, Saturn teaches humility, Saturn teaches wonder. And perhaps, as you drift towards sleep, those are the lessons worth carrying forward. Not the numbers or names, but the feeling of standing small beneath something vast, ancient, and impossibly beautiful. Saturn will still be there tomorrow and the day after, and for billions of years beyond our brief moment of attention. The rings will continue their slow dissolution. The moons will orbit. The storms will rage, all unfolding according to laws we partially understand in a system we've barely begun to explore. Perhaps that's the comfort in contemplating the cosmos, that these vast mechanisms continue regardless of whether we're watching, that Saturn's existence doesn't depend on our understanding, that the universe is larger than any of us and will endure long after we're gone. Rest now. Let Saturn keep its vigil in the outer solar system while you keep yours here, in the warmth, in the light, in this small corner of space where life emerged and consciousness awakened, and we learned to look outward and wonder. The ringed planet will be waiting when you're ready to look again. Good night.